Hello there and welcome. Tonight, we gently drift into the quiet wonder of the Milky Way galaxy, our vast river of starlight. It's a place intricately woven with ancient suns, shaped by powerful cosmic forces, and home to hidden structures far grander than anything our immediate imagination might conjure. Our galaxy, you see, isn't just a simple collection of stars. It is a living, breathing system, meticulously sculpted by billions of years of cosmic history, and perpetually filled with countless mysteries, patiently waiting to unfold. As we embark on this quiet journey, picture yourself moving, very slowly, through that immense expanse. Imagine soft, ethereal clouds of dust, shimmering faintly in the distant starlight. Sense the hidden currents of energy, flowing almost imperceptibly between ancient, colossal objects, while vast clusters of stars drift like silent islands within the endless void. The Milky Way holds countless wonders, each one shaped across unimaginable stretches of time, and each inviting a profound, quiet sense of curiosity. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Now, let's begin our gentle exploration. Our galaxy is so incredibly vast, so utterly immense, that even light itself, the fastest known entity in the universe, requires a staggering 100,000 years just to traverse its diameter. When we imagine light in our everyday lives, we typically picture something impossibly swift, something that slips across a room in an instant, touching our eyes before we even consciously register its movement yet. When that very same light attempts the monumental journey across the Milky Way, it transforms, in a cosmic sense, into something almost ponderously slow by comparison. It would take it an astonishing 100 millennia to travel from one end of our magnificent galaxy to the other. That distance, truly, is so enormous, so profoundly immense, that it stretches the very limits of human imagination, requiring us to contemplate scales far beyond our terrestrial experience. The space between the stars, while often perceived as empty, is not entirely so. It's a diffuse realm, open enough that light travels freely through it, occasionally brushing past microscopic dust grains in the silent, drifting atoms that permeate the interstellar medium. The sheer, overwhelming scale of this journey means that when we gaze deeply into the heart of the Milky Way, we are not, in fact, seeing it as it exists in this precise moment. Instead, we are observing layers upon layers of history stacked across unimaginable distances. The light originating from the most distant regions of our galaxy began its journey long before any human being ever walked upon the Earth. Every faint shimmer, every delicate glint in the night sky carries with it a fragment of ancient time, a relic of epochs long past. It serves as a profound reminder that even the fastest known entity in the universe, light itself, becomes gentle and patient when measured against the monumental, silent size of our cosmic home, unfolding its story across aeons. Now, as we consider such immense stretches of time and space, our journey takes us to the very heart of this vast system. Deep in the core of the Milky Way lies an object of such profound density and power that it cannot be seen directly, yet its omnipresent influence subtly shapes the entire galaxy around it. This is a supermassive black hole, an unseen giant that patiently waits there, cloaked behind swirling clouds of dust and the ceaseless motion of stars that whirl around it at truly incredible speeds. Its gravitational pull is so extraordinarily intense that it actually bends the very fabric of space and time in its vicinity, creating a profound warp in the cosmic canvas. Stars dwelling near this galactic center trace out elaborate, looping paths, their precise motions revealing the invisible, colossal mass that guides their intricate dance. At greater distances from the core, its gravitational influence becomes more gentle, a subtle whisper rather than a roar. But as one approaches the heart, that influence becomes overwhelmingly powerful, an inescapable grip. Gas clouds, vast and diffuse, stretch and twist dramatically as they are inexorably pulled inward, heating up and glowing with a fiery intensity as they spiral down toward the dark, unseen center. Although the black hole itself is utterly silent, emitting no sound and no light, the region immediately surrounding it pulses with a mesmerizing, turbulent activity, all created by the vast amounts of matter rushing into its powerful grasp. This hidden heart serves as the anchor for the entire Milky Way, giving fundamental shape to its grand rotation and helping to bind its countless stars together in a cohesive structure. The very thought of something so unbelievably powerful, and yet so profoundly quiet, an entity that can bend space and time without a single sound or a flicker of light, invites a deep, almost reverent sense of wonder within us. The center of our galaxy is, therefore, far from a calm or tranquil place. Instead, it is a restless, dynamic zone, perpetually ruled by this unseen, colossal giant, a silent orchestrator of cosmic motion. Our galaxy, the Milky Way, carries within its ancient memory a dramatic event from the deep past. It once entirely swallowed a galaxy nearly half its own size. In those primordial epochs, a large companion galaxy drifted too close to our burgeoning Milky Way. Its gravitational bonds proved insufficient to resist the powerful tidal forces exerted by our larger system. Gradually, inexorably, it was pulled apart, its stars, its star clusters, and vast streams of stellar debris slowly absorbed into the sprawling galactic halo, ultimately becoming an intrinsic part of the structure we observe today. Evidence of this ancient, cosmic feast still manifests itself in the form of unusually energetic stars, which move with velocities and trajectories that betray their foreign origins. We also find broad, sweeping arcs of stellar material, like ghosting brushstrokes across the canvas of the sky, that trace the fading remains of that lost system. Astronomers, with their sensitive instruments and meticulous observations, can still identify these fragmented remnants by carefully studying their unique motions and their distinct chemical fingerprints, which differ markedly from those of stars that were originally born within the Milky Way itself. This colossal absorption event may have significantly thickened our galactic disk, stirred the mysterious dark matter halo that envelops us, and even profoundly influenced the development and graceful morphology of our galaxy's iconic spiral arms. It stands as a stark, yet beautiful, reminder that galaxies, far from being static entities, grow and evolve through acts of cosmic consumption, absorbing entire smaller systems over immense, unimaginable stretches of time. The Milky Way we inhabit today, the one we gaze upon with such wonder, carries deep within its structure the enduring remnants of this vanished giant, a ghostly companion whose stars now quietly shine as an integrated part of our own celestial home, their ancient light interwoven with ours. Encircling the magnificent disk of the Milky Way, drifting far beyond its spiral arms, is a quiet, ethereal community of smaller, satellite galaxies. Each of these celestial companions carries within it not only its own stellar population, but also profound memories of a much earlier, more primordial universe. These diminutive galaxies drift in long, graceful orbits around our larger system, some so incredibly faint and diffuse that they blend almost completely into the vast, dark expanse around them like whispers in the cosmic wind. Their stellar populations are often ancient and lightly populated, giving them a fragile, almost translucent appearance, as if they are barely holding themselves together. Yet, despite their apparent delicacy, they play a surprisingly important role in the Milky Way's ongoing evolution. Their slow, deliberate passages tug gently at our galaxy's outer hollow, stirring subtle gravitational waves that ripple imperceptibly through the enigmatic dark matter envelope that surrounds us. Some of these satellite galaxies have already begun the process of shedding their delicate streams of stars, leaving behind pale, shimmering trails that wrap around the Milky Way like ancient, unraveling threads, slowly merging into the larger structure. Studying these quiet companions provides invaluable insights into how large galaxies, like our own, grow and accumulate mass over cosmic timescales. It reveals that this growth doesn't always occur through sudden, dramatic events, but often through countless, gentle gravitational interactions spread patiently across unimaginable spans of time. They move like wise elders circling a great family, each preserving a unique chapter of cosmic history. And in doing so, they deepen our understanding of precisely how the Milky Way became the grand, elegant spiral we know and cherish today. We often perceive our sun as a steady, unmoving anchor in the sky, a warm and familiar point of constancy. Yet, in reality, this perception is far from the truth. Our sun, along with its entire retinue of planets, moons, and every drifting speck of dust that makes up our solar system, is hurtling through the galaxy at a speed far, far beyond anything we can directly experience on Earth. It moves faster than a bullet fired from a rifle, sweeping our entire cosmic neighborhood along with it in a grand, silent procession. Everything you know, every atom, every memory, is riding on this immense, ceaseless motion. The sun follows a vast, curved path around the very center of the galaxy, a majestic orbit guided by the overwhelming force of gravity and meticulously shaped by the collective mass of countless billions of other stars, dark matter, and gas clouds. Even though we cannot physically feel this incredible motion, it is an ever-present reality, subtly shaping the long-term future of our solar system and determining how we, as passengers, drift through the diverse regions of the Milky Way. As the sun continues its epic journey, it quietly encounters diffuse clouds of gas, faint radiation fields, and shifting gravitational currents, all of which subtly influence the immediate space around us. This silent, magnificent voyage has already endured for billions of years, and it is destined to continue for billions more. The profound thought that our familiar, seemingly stationary star is, in fact, an intrepid traveler on an enormous galactic orbit, invites a quiet, deep sense of awe within us. We are, all of us, passengers on a journey that never truly stops, a silent cosmic ballad that unfolds across the vastness of time and space. When most people contemplate the birth of a star, their minds naturally conjure images of intense heat, raging flames, and blazing, uncontrolled energy. The truth, however, is far stranger and more beautiful in its unexpected tranquility. Stars, in their nascent stages, actually begin their lives in enormous clouds that are colder than anything found naturally on Earth. So cold, in fact, that the very concept of fire is an impossibility within them. These primordial clouds are vast, diffuse structures, composed predominantly of dust and gas, gently drifting through the expansive reaches of the Milky Way. To our eyes, they appear as dark, opaque voids because they effectively block the light from the myriad stars behind them. But within their shadowy depths, temperatures plummet to levels where molecules move with an almost imperceptible slowness, gently colliding and gathering. In this frigid environment, gravity, rather than fire, does the initial, painstaking work. It patiently gathers the cold material, pulling it together, slowly, incrementally, until it forms dense, isolated pockets within the larger cloud. As these pockets gradually grow heavier, their internal gravitational pull intensifies, causing them to contract even further. Slowly, through the relentless force of pressure alone, the very center of these collapsing pockets begins to warm. Over incredibly long stretches of time, measured in hundreds of thousands or even millions of years, the temperature within the core steadily climbs. And only when it becomes unimaginably high, reaching millions of degrees, does nuclear fusion finally ignite. That pivotal moment, that gentle internal spark, transforms a silent, cold, shadowed cloud into a brilliant, shining star, bathing its surroundings in its newly awakened light. The profound idea that brilliant, blazing suns begin their lives as chilled, shadowed knots of dust and gas feels almost like a cosmic secret whispered across the vastness. It tells us that creation, even on the grandest scales, often commences in stillness, in quiet repose, long before any light or heat makes its dramatic appearance. The galaxy, in its infinite wisdom, forms its new stars in these tranquil, almost hidden places where intense heat is, initially, merely a distant, future dream, waiting for gravity to orchestrate its slow, magnificent arrival. We, and our entire solar system, float within a giant, ethereal bubble, a vast cavity carved out of the interstellar medium by the powerful echoes of ancient stellar explosions. This incredible structure surrounds us, yet we traverse it daily without ever consciously noticing its presence. Long before the first humans walked the Earth, powerful stars situated near our region of the galaxy lived fast, incandescent lives and met their ends in cataclysmic, explosive deaths. These supernovae, with their immense energy, pushed away enormous amounts of gas and dust, effectively clearing out a wide, spherical area of space. The magnificent result is this giant, shimmering bubble that now encompasses our entire solar system. This bubble is not truly empty. Rather, it is filled with thin, incredibly hot gas, a direct legacy created by the shock waves of those ancient supernovae. The material within this bubble is far less dense than the gas found in other, more crowded regions of the Milky Way. Our Sun and its accompanying planets drift comfortably and serenely within this airy, warm region, moving through it as if passing through a quiet, cosmic room left behind by those long-vanished, violent events. The edges of this colossal bubble are shaped like walls, composed of cooler, denser gas, where the remnants of those powerful explosions finally slowed down and accumulated. Astronomers, using sophisticated instruments, can meticulously map this grand, invisible structure by tracing the faint X-ray light emitted by the hot, diffuse gas inside it. Realizing that our entire solar system, our familiar home, sits quietly within the lingering remains of long, vanished stellar giants brings a soft, humbling, and utterly unique perspective to our place in the cosmos. We are, in essence, surrounded by the quiet echo of ancient cosmic events, powerful forces that profoundly shape the very space we now comfortably call home. Galaxies, though they may appear serene and unchanging when viewed from the immense distances of intergalactic space, are in truth dynamic, ever-evolving structures that continuously interact, merge, and transform over vast stretches of cosmic time. The Milky Way, our own majestic home, is certainly no exception to this grand cosmic ballet. It is, even now, slowly but inexorably drawing in several smaller, less massive galaxies that orbit nearby, trapped within its immense gravitational sphere of influence. The stars from these unfortunate, smaller companions are stretched and pulled into long, delicate streams that gracefully wrap around our larger galaxy like shimmering, ethereal ribbons. These stellar streams, faint yet persistent, serve as poignant visual revelations of the paths taken by the smaller galaxies as they are gradually, relentlessly torn apart by the Milky Way's overwhelming gravitational tides. Gravity, in its quiet, persistent way, pulls them in bit by bit, star by star, until their individual suns eventually become an integrated, indistinguishable part of the Milky Way itself. This process of galactic consumption has occurred many times throughout our galaxy's long history, and it is destined to continue far into the future, as new dwarf galaxies inevitably wander too close. This ongoing process of absorption helps to explain the widespread presence of ancient, odd star clusters and unusual stellar populations scattered throughout the Milky Way, their origins betraying their foreign heritage. Our galaxy grows and expands through these ancient mergers, steadily absorbing the remains of its smaller, less fortunate companions, much like a grand cosmic river drawing in smaller tributaries. Even in this very epoch, faint galaxies like the Sagittarius dwarf spheroidal galaxy are in the process of being pulled apart, their stars gradually falling inward, destined to become part of our own sprawling stellar disk. The profound idea that our majestic galaxy is continuously shaped by a long history of gentle, yet relentless, cosmic cannibalism feels both strange and utterly fascinating. It serves as a powerful reminder that even structures as inconceivably vast and seemingly stable as galaxies are perpetually influenced by the quiet, insistent pull of gravity, an unseen hand orchestrating their destinies. The Milky Way holds within its ancient embrace stars that formed long before Earth ever came into existence. Some of these venerable celestial bodies are more than twice as old as our own planet, providing an invaluable glimpse into the very earliest days and formative years of the galaxy. These truly ancient stars carry within their atomic structures unique chemical signatures, which act as cosmic time capsules, revealing what the universe was like shortly after the first generations of massive stars lived their brief, brilliant lives, and then died in cataclysmic explosions. Crucially, these old stars contain significantly fewer heavy elements beyond hydrogen and helium, because those heavier elements had not yet been created in large quantities by the supernovae of earlier stellar generations. Their light is subtly different, their atmospheres simpler in composition, and their stories, etched in their very being, are immeasurably longer than our own suns. Many of these primordial stars drift serenely in the galactic halo, a sparse, spherical region that envelops the main disk of the Milky Way. They move on elongated orbits that take them high above and far below the more crowded spiral arms. Observing these ancient suns allows astronomers to study the early universe in a quiet, direct, and remarkably profound way. These venerable stars have burned steadily for billions of years, holding within their cores the secrets from a time when the galaxy was still fresh and new, coalescing from the primordial gas and dust. Their enduring existence adds a deep, almost comforting sense of continuity to the cosmic narrative, a powerful reminder that long before our world took shape, the Milky Way was already shining with the gentle, persistent light of its very earliest stars, illuminating the nascent universe. When we look up at the Milky Way on a clear, dark night, far from the light pollution of our cities, we perceive a glowing, hazy band stretching majestically across the sky. Much of that soft, diffuse glow emanates from countless stars so incredibly faint, so individually dim, that even the most powerful telescopes cannot resolve them as distinct, individual points of light. These stars are typically small and dim, often red dwarfs or sub-dwarfs, but their sheer numbers are incredibly vast, almost beyond comprehension. Their combined, collective light forms a soft, pervasive background illumination that fills the entire disk of the galaxy, like a gentle, internal luminescence. Furthermore, the omnipresent dust and gas within the galactic plane scatter and diffuse this composite starlight, contributing to the Milky Way's characteristic hazy, ethereal appearance. Even though these faint stars are individually invisible to our current observational capabilities, their collective mass and luminosity contribute significantly to the overall mass and intricate structure of the galaxy. They help to shape the gravitational pull that subtly guides the motion of their brighter, more prominent stellar siblings. Some of these faint stars are ancient red dwarfs, patiently burning their fuel slowly and quietly, destined to exist for trillions of years. Others are young, nascent stars, just beginning their incredibly long lives, slowly gathering mass and preparing for their own luminous destinies. The profound idea that our galaxy shines with the collective, gentle breath of countless unseen suns, each too dim to be individually resolved, creates a quiet, almost poetic feeling of mystery and vastness. The light we perceive, therefore, is not merely the brilliant glow of a few prominent, bright stars, but rather the soft, harmonious chorus of multitudes, a myriad of distant suns that whisper their collective light across the immense, silent canvas of the sky. Not all planets in the vast expanse of the Milky Way are bound in predictable orbits around a parent star. Some worlds move freely and silently through space, drifting alone through the profound darkness of interstellar regions. These enigmatic celestial bodies are known as rogue planets, and they were most likely born within nascent solar systems, much like our own, but were later violently cast out. This ejection usually occurs due to powerful, chaotic gravitational interactions with other, more massive planets, or even the central star itself, during the turbulent early stages of their system's formation. Without the warmth and light of a sun to illuminate and heat them, these rogue planets traverse the galaxy in a state of deep, perpetual cold. Their surfaces are undoubtedly frozen, locked in an eternal icy embrace. Yet, beneath these frigid exteriors, some of these lonely wanderers could potentially harbor warm, liquid interiors, heated by the lingering radioactive decay of elements within their cores or by internal tidal stresses. The very idea of entire planets wandering alone, unbound and unmoored, evokes a haunting sense of quiet beauty and cosmic solitude. These worlds do not follow predictable, elliptical orbits. Instead, they move on incredibly long, solitary paths shaped only by the diffuse, gentle gravity of the galaxy itself. They may pass fleetingly near other stars, slip silently through dense star clusters, or disappear entirely into the vast, dark emptiness of the galactic halo. Although they are incredibly difficult to detect, given their lack of self-illumination and reflected starlight, their presence is strongly predicted by sophisticated astronomical simulations and hinted at by faint, indirect observations such as microlensing events. Indeed, there may be far more of these silent, wandering worlds than there are planets that orbit stars, populating the vast, dark spaces between the stellar nurseries. Thinking of these silent travelers, drifting endlessly through the Milky Way, invites a calm, almost meditative sense of wonder. In the vast, dark, and often overlooked spaces between the blazing stars, entire worlds glide unseen, cold and utterly solitary, carrying their own hidden stories through the eternal night, profound and mysterious in their isolation. Far beyond the iconic spiral arms of the Milky Way, extending outward into the truly immense cosmic void, lies a massive, diffuse halo composed of extremely hot gas. This ethereal halo extends for vast distances, both above and below the relatively thin galactic disk, enveloping our entire home galaxy like an unseen, colossal atmosphere. The gas within this halo is heated to temperatures far, far hotter than any flame found on Earth, reaching millions of degrees. It becomes so highly energized that it emits faint X-ray light, a silent, invisible glow that bathes the outer reaches of the galaxy. Although this gas is incredibly tenuous and thin, almost a perfect vacuum by terrestrial standards, it contains enough collective mass to subtly influence the motion of stars in the outer regions, and even the trajectories of the smaller satellite galaxies that orbit the Milky Way. This halo is believed to be a primordial leftover from the earliest stages of the Milky Way's formation, a relic from when the galaxy first coalesced. Additionally, it is continuously replenished and heated by the ongoing activity of supernovae explosions within the galactic disk, which powerfully push material outward into this expansive envelope. Furthermore, this hot halo also acts as a vast reservoir of matter, a cosmic well that may one day slowly fall back into the main body of the galaxy, potentially fueling new rounds of star formation in the distant future. The halo, though invisible to our normal sight, nonetheless surrounds everything we know, every star, every planet, every nebula. It serves as a powerful reminder that the Milky Way is not simply a flat, two-dimensional disk of stars, but rather a layered, intricate, and deeply three-dimensional structure with components that stretch far into the surrounding space. This hot, quiet, and invisible atmosphere envelops our galaxy like a vast, ancient cloud, a silent guardian composed of energized particles. Across the immense canvas of the Milky Way, ancient, cataclysmic explosions leave behind enduring signals, subtle echoes that travel far beyond the visible light from their shattered stellar shells. These remarkable signals manifest as radio waves, gentle in their tone, but incredibly powerful in their reach, traversing vast cosmic distances. When a massive star reaches the end of its life and collapses into a supernova, the colossal blast sends powerful shock waves, rippling outwards through the surrounding space, like an expanding sphere of cosmic energy. These shock waves intensely energize the diffuse interstellar gas they encounter, causing it to glow faintly, but persistently in specific radio frequencies. These radio emissions can then cross vast distances without quickly fading, allowing astronomers to detect them across the galaxy. Even long after the brilliant, visible light of the initial explosion has dimmed and vanished, the radio glow remains, drifting quietly through the galaxy as a lingering testament to the star's dramatic demise. Astronomers utilize incredibly sensitive radio telescopes and instruments to painstakingly trace these faint echoes, meticulously mapping the intricate structure of old supernova remnants that are often hidden deep inside dusty, opaque regions of the galaxy, invisible to optical light. Each ripple in these radio emissions carries invaluable information about the immense force of the original explosion, the dynamic shape of the expanding cloud of debris, and the specific types of materials that were violently released into space, enriching the interstellar medium. These radio waves thus reveal the hidden history of countless stellar deaths that once enriched the galaxy with heavy elements. The very building blocks of planets, and indeed of life itself. They allow us to study events far older than humanity, reaching back into eras when entire regions of the Milky Way looked dramatically different, shaped by a relentless cycle of stellar birth and death. In this soft, pervasive radio light, the galaxy quietly speaks of its deep and complex past, whispering memories of stars that lived brightly, burned furiously, and then ended their luminous journeys in dramatic, yet ultimately silent, explosions. Among the densest and most extreme objects known in the universe are neutron stars. These incredible celestial bodies are formed when truly massive stars, far more substantial than our Sun, collapse in on themselves after undergoing a supernova explosion. The matter within their cores becomes so extraordinarily tightly packed, so intensely compressed, that ordinary atoms, as we understand them, simply cannot survive. Under this unimaginable pressure, the protons and electrons within the atomic nuclei are forced to merge, transforming into neutrons, thus creating a substance unlike anything we could ever encounter or recreate on Earth. To illustrate this mind-boggling density, consider this if you could, hypothetically, take a single teaspoon of this neutron star material, an act no human could ever actually perform. It would possess a mass greater than that of an entire mountain on Earth. This unimaginable density fundamentally reshapes the way light, magnetism, and gravity behave in the immediate vicinity of a neutron star. These remnants of once mighty stars often spin with astonishing rapidity, some rotating hundreds of times per second, sending out focused beams of radiation that sweep across space like cosmic lighthouses. They also generate magnetic fields that are billions of times stronger than anything produced by human technology. Fields so powerful they could potentially distort the very structure of atoms. Their surfaces are believed to be incredibly smooth, with gravity so intense that even a small bump or irregularity could not exist for long, being immediately crushed flat. These strange, exotic remnants cool excruciatingly slowly over millions of years, gradually fading as they release their trapped internal heat into the void. Studying them helps scientists to understand the fundamental limits of matter and the extreme conditions that exist in the most violent corners of the cosmos. The profound thought that so much mass, such an incredible amount of material, can be compressed into such an unimaginably tiny space inspires a deep and humbling sense of wonder. Neutron stars serve as potent reminders that the universe holds states of matter and physical phenomena far, far beyond our everyday experience, constantly challenging our understanding of reality. Throughout the vast, star-strewn expanse of our galaxy, long, delicate chains of stars drift together along graceful, gentle arcs, like ancient, winding rivers flowing through the cosmic landscape. These magnificent star streams are, in fact, the lingering remains of smaller galaxies and compact star clusters that were once distinct, cohesive entities, but were slowly and relentlessly pulled apart by the powerful, inexorable gravitational tides of the larger Milky Way. As these smaller systems were stretched and torn, their constituent stars scattered along their original orbital paths, forming sweeping, elongated trails that can span truly great distances across the sky. Although these streams are often faint and diffuse, making them challenging to observe, they act as invaluable records of the Milky Way's tumultuous past interactions. By meticulously studying their precise shapes, their subtle motions, and the chemical compositions of their stars, astronomers can reconstruct the detailed histories of the smaller galaxies and clusters that contributed them, understanding how they met their cosmic fate. Some of these streams curve high above the galactic disk, tracing vast, looping trajectories through the halo, while others flow quietly and almost imperceptibly within the crowded galactic plane itself. They collectively reveal how the omnipresent force of gravity sculpts the intricate structure of the Milky Way over immense periods of time, continuously redistributing stars across enormous, galactic scales. These delicate, ribbon-like formations also provide a crucial tool for scientists to map the invisible dark matter halo that surrounds our galaxy. The precise paths of the stars within these streams trace the contours of the gravitational field, allowing researchers to infer and understand how unseen mass, the mysterious dark matter, shapes their complex motion. In a quiet, profound way, star streams unequivocally demonstrate that the Milky Way is a constantly evolving, dynamic system. They carry within them the silent memories of ancient galactic encounters, stretched across the sky like soft, luminous reminders of our galaxy's long, complicated, and ever-changing history. Across the vast, sprawling disk of the Milky Way, the process of star formation never truly ceases. It is a continuous, vibrant cycle of cosmic renewal. In cold, shadowed clouds of gas and dust, scattered generously throughout the majestic spiral arms, new stars are perpetually emerging. This happens as gravity, the fundamental sculptor of the cosmos, patiently pulls the diffuse gas together into increasingly dense pockets. These nascent pockets, known as protostars, slowly but inexorably compress under their own immense weight until their internal temperatures and pressures rise high enough for the miraculous process of nuclear fusion to begin deep within their cores. That pivotal moment, that gentle internal spark, marks the true birth of a star, its internal furnace now ignited. Although it may seem incredible to our human perception, this process occurs so frequently and so consistently across the vast, sprawling disk of the galaxy that, on average, new stars are igniting every single second. Some of these newborns are tiny, long-lived red dwarfs, destined to burn quietly and steadily for trillions of years, far outliving the current age of the universe. Others are much larger and significantly brighter, living fast, brilliant lives, destined to end dramatically in powerful, cataclysmic supernovae, enriching the galaxy with heavy elements. The precise locations where this ceaseless star formation occurs are intricately shaped by a complex interplay of cosmic turbulence. The subtle influence of magnetic fields and the recycled leftover material from older generations of stars that have already lived and died. The intense light and energetic winds from newly formed stars gradually clear away the surrounding dust and gas, revealing the luminous clusters that shine brightly against the darker background of space. These young, energetic stars also profoundly influence their environment by sending out powerful, energetic stellar winds, which sculpt and reshape the very clouds of gas and dust that created them. The continuous birth of stars is one of the most fundamental processes that keeps the Milky Way alive, dynamic, and perpetually vibrant. It ensures that even as older stars gracefully fade and eventually die, new sources of light and energy are always appearing, maintaining the galaxy's luminous splendor and providing the raw materials for future generations of planets and, perhaps, even life. In the Milky Way, there exists a fascinating class of stars that rotate with astonishing, almost dizzying speed. Their equators can move at hundreds of kilometers per second, a velocity far exceeding the leisurely rotation of our own Sun. If not for the immense, crushing pull of their own gravity, these rapidly spinning stars would literally tear themselves apart, unable to contain their centrifugal forces. This incredibly rapid spin causes them to visibly bulge outward at their middles, forming distinctly flattened, oblate spheroids rather than the perfect spheres we often associate with stars. This dramatic distortion in shape subtly affects the temperature distribution across their surfaces, making their poles significantly hotter and brighter than their extended equators, a phenomenon known as gravity darkening. The fast rotation can also lead to the generation of incredibly strong and complex magnetic fields, and it profoundly affects how material flows around them, influencing stellar winds and accretion disks. Some of these rapidly rotating stars are known to eject vast amounts of gas into the surrounding space, creating shimmering disks or graceful rings that glow softly, a testament to their dynamic nature. Their incredible speed profoundly influences how they evolve over time, affecting how efficiently they burn their nuclear fuel, and, ultimately, how they will eventually meet their end. Observing these rapid rotators helps astronomers understand the fundamental limits of stellar physics, revealing just how fast a star can spin before it begins to break apart or dramatically change its structure. These extreme stars offer a captivating glimpse into a more intense, high-energy side of the Milky Way, where the delicate balance between gravity and rotational motion is maintained with astonishing precision. They clearly demonstrate that even stars, seemingly stable and serene, can experience profound tension between their inherent stability and the powerful forces that relentlessly push them outward, shaping their very being. Not all regions of the galaxy are uniformly filled with the brilliant glow of stars and the diffuse presence of gas. Some areas are surprisingly, profoundly empty, vast cosmic voids carved out by ancient, energetic events that swept material away over immense periods of time. These enormous cavities, like colossal bubbles within the interstellar medium, can span hundreds of light years across, leaving behind silent, rarefied pockets of thin space deep inside the crowded spiral arms. Many of these grand voids were created by clusters of massive, short-lived stars whose intense stellar winds and powerful supernova explosions collectively pushed outward, clearing large sections of the surrounding gas and dust. Over millions of years, these energetic blasts hollowed out individual bubbles that subsequently merged and coalesced into even larger, more expansive voids. Although these regions contain significantly fewer particles than their surrounding environments, they are still subtly influenced by the gentle pressure of nearby gas and the pervasive gravitational pull of the galaxy itself. Studying these enigmatic cavities helps astronomers to understand how the immense energy released by dying stars profoundly shapes the structure and evolution of the Milky Way. They reveal where clusters of massive stars once lived and died, and how their collective activity influenced the surrounding interstellar environment, triggering or halting subsequent star formation. These vast pockets of emptiness stand in stark contrast to the dense, dark molecular clouds that serve as the cradles of new stars. They serve as a quiet, compelling reminder that the galaxy is not a uniform or monotonous entity, but rather a complex, dynamic system shaped by ongoing cycles of creation and destruction, each leaving its indelible mark in the form of both bright, bustling birthplaces and quiet, hollowed-out gaps in the star-lit landscape. Among the many strange and wonderful planets scattered throughout the Milky Way, some worlds are theorized to be so incredibly rich in carbon that their deep interiors may form vast, glittering layers of diamond-like structures. These exotic diamond worlds likely developed in regions of the galaxy where the raw materials available during their formation were significantly different from those found near our Sun. Instead of being dominated by common silicates and metals, these planets are believed to contain exceptionally high amounts of carbon, which, under the intense pressures found in their deep interiors, can transform into solid, crystalline structures remarkably similar to diamond. While their surfaces might appear dark and rocky, beneath lies a geological landscape shaped by exotic, high-pressure chemistry, a hidden treasure trove. These unique planets can orbit either very close to their parent stars or drift much farther away, depending on the specific conditions of their formation. Studying them helps scientists to understand the incredibly wide variety of planetary compositions and conditions that exist across the galaxy, revealing that planets can differ dramatically from those found in our own familiar solar system. Imagining entire worlds constructed from carbon-rich materials, with glittering, diamond-like layers hidden just beneath their crusts, offers a quiet, almost fairy tale-like sense of wonder. These hypothetical diamond worlds reveal that the Milky Way holds forms of planetary beauty and geological grandeur far beyond anything we have yet encountered or even conceived of on Earth, expanding our understanding of cosmic diversity. Some stars within our galaxy are capable of unleashing sudden, violent bursts of energy that can dramatically dwarf the normal output of their steady stellar activity. These potent bursts can occur when the incredibly powerful magnetic fields on the star's surface become twisted, tangled, and then suddenly snap and reconnect, releasing enormous amounts of stored magnetic energy in the form of fierce radiation. The energy released during such a stellar flare can be so intense that it would be capable of stripping away the atmospheres from any nearby planets or drastically altering their surfaces, rendering them barren and lifeless. While these extreme events are relatively rare, they powerfully demonstrate just how unstable and unpredictable certain types of stars can be. The bursts travel through space as incredibly intense flashes of light and high-energy particles, propagating at nearly the speed of light. Even from vast distances, they can be detected by sensitive astronomical instruments, providing crucial data. Studying these dramatic outbursts helps astronomers understand the complex magnetic behavior of stars and the dynamic, often violent, environments that surround them. Many of these flare stars are young and still in the process of settling into stable patterns of rotation and energy output. Others are older but possess unusually strong or erratic magnetic fields that lead to these periodic eruptions. These sudden, powerful stellar eruptions serve as a potent reminder that stars are not always perfect, serene spheres of calm, steady light. They can be dynamic, unpredictable, and even violent, sending out powerful pulses of energy that profoundly reshape the space around them and dramatically alter the fate of any orbiting worlds. While our solar system contains a modest and well-ordered number of planets, the Milky Way holds countless other systems that are far more crowded and complex. Some stars, it turns out, are orbited by dozens of planets, each following its own intricate path through the vastness of space. These highly populated systems typically form when exceptionally large and dense disks of gas and dust collapse around young stars. The abundant material within these massive disks gathers into numerous clumps that, over long periods, gradually grow into fully formed planets. Because these protoplanetary disks are so vast and rich in material, they can produce far more worlds than the relatively smaller and less dense disk that gave rise to Earth and our solar system. These multitudinous planets can vary wildly in size, from small, rocky bodies to massive gas giants. They can be icy and distant or fiery and close to their star. Their complex gravitational interactions create intricate, dynamic patterns that can shift and evolve over immense periods, leading to a perpetual, slow-motion cosmic dance. Studying these incredibly rich and diverse planetary systems helps astronomers understand how planets form under a wide array of different conditions and how planetary architecture can be incredibly varied, even within a single stellar system. The profound idea that some stars host entire families of planets far larger and more diverse than our own significantly adds to the sense of abundance and limitless possibility within the Milky Way. It suggests that our galaxy may hold endless varieties of worlds, each with its own unique characteristics and histories, patiently waiting to be discovered and understood. Not all stars remain peacefully where they were born, quietly orbiting the galactic center for billions of years. Some, in a dramatic twist of fate, experience gravitational interactions so incredibly strong and violent that they are flung out of their original stellar systems and sent wandering alone through the galaxy, like cosmic exiles. This can occur in crowded star clusters where stars pass perilously close to one another, their combined gravity acting like a cosmic slingshot. Alternatively, it might happen when a star's binary companion explodes in a supernova, abruptly altering the delicate balance of gravitational forces and sending the surviving star hurtling away. Once violently kicked out, these stars embark on long, solitary paths through the galaxy. They typically move much faster than most other stars, slipping silently through the spiral arms and drifting into the quieter, more diffuse regions of the galactic halo, or even beyond. Although they may appear as ordinary, shining points of light, their extraordinary motions betray their unusual and often dramatic histories. Studying these runaway stars provides invaluable insights into the dynamic processes of stellar systems and the powerful, chaotic forces that can disrupt them. These lone travelers offer a rare, fleeting glimpse into the more turbulent moments of the galaxy's past. They show us that even stars, seemingly immutable and eternal, can be violently uprooted by powerful cosmic events, sent off on incredible journeys that will take them far from their places of origin, forever changing their destiny within the vastness of the Milky Way. In certain specific regions of the Milky Way, stars gather so incredibly tightly that the individual boundaries between them seem to vanish, blurring into a single, brilliant expanse of light. These are star clusters, and they form when massive clouds of gas and dust collapse simultaneously, giving birth to hundreds or even thousands of stars all at once. Because they are born together, in a single, colossal event, they remain gravitationally bound and relatively close to one another for very long periods, before eventually and slowly drifting apart, dispersed by galactic tidal forces. Inside these young, vibrant clusters, individual stars can be separated by distances far smaller than the vast gaps between stars in the more diffuse regions, such as our Sun's neighborhood. Their combined, dazzling light blends into a brilliant, almost overwhelming glow that would entirely fill the night sky if viewed from a planet orbiting within such a crowded stellar community. Some of these clusters are remarkably spherical, with stars packed most densely towards their very centers, creating a luminous core. Others form looser, more irregular associations, yet still shine brightly through the pervasive dust and gas of the galaxy, acting as beacons in the night. Studying these clusters reveals intricate details about stellar evolution because the stars within them, having formed simultaneously, share similar ages but possess a wide range of different masses. Observations of these stellar nurseries allow astronomers to witness how stars change and evolve as they grow, age, and eventually fade. Clusters also play a profoundly important role in shaping their surrounding environments. Their powerful collective radiation and energetic stellar winds carve out vast cavities in the surrounding gas, influencing where future generations of stars will form, either triggering new birth or dispersing the necessary material. These crowded stellar communities serve as a beautiful reminder that many stars are born not in solitary isolation, but in bright, bustling neighborhoods, glowing with a shared, collective light, their destinies intertwined from their earliest moments. Across the sprawling expanse of the Milky Way lie enormous molecular clouds, truly vast structures composed predominantly of hydrogen molecules intricately mixed with microscopic dust grains. These colossal clouds are among the coldest and darkest places in the entire galaxy, appearing as opaque, shadowy voids against the backdrop of starlight. Yet, despite their frigid, dark appearance, they hold an extraordinary, almost incomprehensible potential. A single, large molecular cloud can contain enough raw material, enough gas and dust to form thousands of stars the size of our Sun, or even more. Their immense collective mass allows gravity to patiently sculpt them into dense, collapsing knots, within which new stars eventually take form. These knots slowly contract and collapse over immense periods of time, gradually heating up until nuclear fusion finally ignites deep within their cores, bringing forth new suns. Despite their truly colossal scale, molecular clouds are, in certain subtle ways, quite fragile. Intense radiation from nearby massive, hot stars can relentlessly erode their surfaces, slowly dispersing their material. Conversely, powerful shock waves from supernova explosions can compress them, dramatically triggering new, rapid rounds of star formation, acting as a cosmic catalyst. Many of these magnificent clouds stretch for hundreds of light years, winding gracefully through the spiral arms of our galaxy like shadowed, cosmic highways of future starlight, quietly awaiting their moment of creation. They are absolutely essential to the ongoing life cycle and continuous renewal of the galaxy, holding within their depths the pristine ingredients for countless new solar systems. Observing them requires specialized instruments, particularly radio and infrared telescopes, because they are entirely opaque to visible light, their secrets hidden behind thick veils of dust. Inside these dark, cold cradles, entire clusters of stars wait patiently to be born, silently hidden from our view until their collective light grows strong enough to pierce through the surrounding gas, announcing their arrival to the wider galaxy. There are stars in the Milky Way whose light does not shine with a constant, unwavering brilliance, but instead rises and falls in rhythmic, almost mesmerizing cycles, like celestial heartbeats pulsing across the vastness. These are known as pulsating stars, and they physically expand and contract as their internal layers subtly shift under the immense influence of heat and pressure within their cores. Each subtle change in their physical size directly alters the amount of light they emit, creating a distinctive pattern of brightness variation that can last for hours, days, or even months, depending on the star's characteristics. These regular, predictable pulses act like a cosmic heartbeat, revealing intricate details about the stars' interiors that cannot be directly observed. By meticulously studying the precise timing and strength of these pulsations, astronomers can accurately determine a star's mass, its precise age, and its surface temperature. Some of the most well-known pulsating stars, such as Cepheid variables, are incredibly valuable and are used as cosmic distance markers, because their brightness patterns follow highly predictable rules, allowing for precise measurements. These stars are crucial tools, helping astronomers to map the intricate, three-dimensional structure of the Milky Way by providing reliable distance measurements for incredibly distant regions that would otherwise be impossible to gauge. Pulsation can occur in a wide variety of stars: young, newly formed stars, aging giants nearing the end of their lives, or stars in transitional stages of their evolution. Each category exhibits its own unique, characteristic rhythm, a distinct stellar signature. The gentle, rhythmic flickering of these stars adds a quiet, almost poetic sense of movement and vitality to the galaxy, reminding us that even seemingly stable points of light can contain complex, dynamic rhythms deep within their glowing, turbulent layers, a silent song echoing across the cosmos. Long after a powerful supernova explosion fades from visible view, its initial, colossal shock wave continues its relentless journey outward, expanding through the galaxy. These waves sweep through the Milky Way like ever-expanding ripples across a cosmic pond, silently carrying the immense energy of the original explosion far across interstellar space. As they travel, they dynamically compress existing gas clouds, subtly heat the diffuse interstellar material, and leave behind faint, yet profound, changes in their wake. Some shock waves move through regions already filled with dust, sculpting it into new, intricate shapes and patterns, much like a cosmic artist. Others pass through more empty areas, gradually weakening with distance, yet still preserving the faint memory of their violent origins, a ghost of a past cataclysm. These shock waves can take tens of thousands of years to expand to their full, enormous size, traversing vast distances. Along their protracted journey, they can powerfully trigger new rounds of star formation by compressing cold, stable regions of gas, forcing them past the critical density required for gravitational collapse. They also crucially enrich the interstellar medium with the heavy elements that were forged inside the supernova, the building blocks for future stars, planets, and even life itself. Modern telescopes, equipped with sensitive detectors, can detect these invisible shock waves by observing the faint X-ray and radio emissions they produce as they interact with the interstellar medium. They appear as expanding, ethereal shells or delicate, glowing filaments that reveal the intricate structure of the surrounding space, a cosmic fingerprint. Even though the star that created them may be long gone, its profound influence continues to travel quietly through the galaxy, shaping the environment for future generations of stars, a silent legacy. The pervasive dust that fills the Milky Way has a dramatic and deeply interconnected origin. Much of it was not primordial, but rather forged in the outer, cooler layers of aging stars as they reached the very ends of their luminous lives. As these stars expanded dramatically into red giants, their vast outer atmospheres cooled sufficiently for tiny, solid particles, known as dust grains, to begin to form. When these dying stars subsequently shed their outer envelopes, gently or violently, these newly formed particles escaped into the vastness of space, becoming part of the interstellar medium. Other types of dust were created during the cataclysmic explosions of massive stars in supernovae, which violently released freshly formed heavy elements into the interstellar medium, where they condensed into dust. Over immense stretches of time, these dust grains drifted throughout the galaxy, becoming essential ingredients in the ongoing formation of new stars and planets. They play crucial roles. They help cool collapsing gas clouds, allowing them to contract further. They shield delicate molecules from harmful radiation, and they provide crucial surfaces upon which complex chemical reactions can occur, laying the groundwork for more intricate structures. Dust both absorbs and scatters starlight, giving the Milky Way its soft, diffuse glow and dramatically shaping the appearance of the vibrant nebulae we observe. Each microscopic grain of dust carries within it the silent legacy of the star that created it, a tiny, particulate echo of a past life. The profound thought that the dust permeating our galaxy, and indeed even the dust that eventually coalesced to form our own Earth, came from the dying breaths of ancient stars, adds a gentle, almost spiritual sense of connection to the larger, cyclical processes of cosmic life and death. It highlights our intimate connection to the grand, ongoing story of the universe. Near the very center of the Milky Way lies an incredibly dynamic region where the force of gravity grows exceptionally strong, a powerful cosmic well. In this dense, extreme environment, a handful of stars orbit with extraordinary speeds, moving far, far faster than stars located in the more distant, tranquil spiral arms. These rapid, almost dizzying motions were first detected through meticulous tracking of each star's precise position over many years of observation. Their incredibly tight, fast orbits provide compelling, undeniable evidence for the presence of a supermassive black hole at the very core of our galaxy, a cosmic behemoth whose immense gravity dictates their every turn. As these stars swing perilously close to the galactic center, they follow sharply curved paths, dramatically shaped by the intense, overwhelming gravitational forces of the central black hole. Their precise motion allows astronomers to accurately calculate the mass of the unseen object controlling their orbits, a powerful testament to the laws of celestial mechanics. These stars also help to reveal the intricate, complex structure of the central region itself, which is densely filled with swirling clouds of gas, powerful magnetic fields, and intense radiation, making it one of the most extreme environments in the galaxy. Despite these incredibly harsh conditions, the stars themselves remain remarkably stable, shining quietly and steadily as they trace their dramatic, high-speed paths around the invisible giant. Observing them requires advanced infrared telescopes, capable of seeing through the thick, obscuring dust that completely surrounds the core and blocks visible light. Their incredible speed and orbital precision offer a rare, invaluable insight into one of the most mysterious and extreme areas of the Milky Way, a place where space and time are profoundly warped by an immense, almost unimaginable gravitational power. As starlight embarks on its long journey through the galaxy, it can pass perilously close to regions of highly concentrated mass. These areas might be dense clusters of stars, invisible structures of dark matter, or even vast collections of gas that are far more massive than they appear in visible light. When light traverses through such incredibly dense regions, the force of gravity subtly bends its path, much like a lens. This gravitational bending creates distortions that can magnify, stretch, or subtly shift the apparent position and appearance of distant objects, a phenomenon known as gravitational lensing. In the Milky Way, this lensing effect allows researchers to detect objects that are otherwise completely invisible, including rogue planets drifting freely through space without a star, and compact stellar remnants like black holes or neutron stars hidden deep within dark, opaque areas. It also helps astronomers to precisely measure the distribution of mass throughout the galaxy, revealing how much of it is composed of normal, visible matter and how much is made of the elusive, mysterious dark matter. The subtle warping of starlight profoundly demonstrates that the universe is not a simple, flat, or empty place. Even the light that eventually reaches our eyes has been intricately shaped and influenced by the complex, invisible landscape of gravity it traveled through. This quiet, almost imperceptible bending of light creates a profound sense of depth and complexity, reminding us that every view of the night sky carries subtle, ancient traces of the invisible structures that fill the vastness of the Milky Way. Throughout the Milky Way, high-energy particles are constantly accelerating through space, traversing immense distances. These particles, collectively known as cosmic rays, originate from some of the most violent and energetic phenomena in the galaxy, including powerful supernovae explosions, highly energetic stars, and turbulent, swirling magnetic fields. They travel at nearly the speed of light, moving freely across vast, intergalactic distances. Even though Earth is significantly protected by its robust atmosphere and powerful magnetic field, a steady, continuous stream of these cosmic rays constantly reaches our planet at all times. Most of them are harmless, interacting with molecules in the upper atmosphere and creating showers of secondary particles that never reach the ground. Studying cosmic rays allows scientists to understand the incredibly energetic processes occurring throughout the galaxy. Their immense energies reveal invaluable information about the violent events that created them, acting as messengers from the cosmos. They also help to map the complex, invisible magnetic fields that thread through the galaxy, since the paths of cosmic rays are bent and deflected as they move through these magnetic structures. Although invisible to our senses, their presence is constant and pervasive, forming a quiet, energetic background of activity around our planet. Cosmic rays demonstrate that Earth is not an isolated oasis in space, but rather intimately connected to the energetic, dynamic workings of the entire galaxy. They provide a subtle, yet powerful, reminder that the Milky Way is a vibrant, dynamic environment, perpetually filled with high-energy particles and powerful forces that reach even our small, blue world, connecting us to the grand cosmic drama. Certain stars in the Milky Way radiate such intense heat and powerful ultraviolet light that they can gradually, but relentlessly, remove the atmospheres of any planets orbiting too closely. These are often young, massive stars, burning with an incandescent brilliance and releasing powerful, continuous winds of charged particles like a cosmic sandblaster. When a planet is exposed to this constant, fierce flow of energy, its upper atmosphere begins to heat up dramatically and then escapes into space atom by atom, molecule by molecule. Over long periods, spanning millions of years, the planet can lose much of its original air, eventually leaving behind a barren, airless surface, completely stripped of its protective envelope. This extreme process helps to shape the long-term evolution of planetary systems, particularly those in close proximity to their parent stars. Some planets may initially form with thick, substantial atmospheres, but gradually, over eons, they become dry and airless due to this relentless stellar erosion. Observing these dramatic interactions allows astronomers to understand how stars profoundly influence the potential habitability of surrounding worlds, determining whether they can retain an atmosphere and, thus, potentially liquid water. It also reveals how planetary atmospheres change and evolve over time in radically different stellar environments. Even though the process is slow and imperceptible on human timescales, the profound idea that a star's intense, unyielding heat can reshape an entire planet, transforming its very essence, adds a powerful, almost fearsome sense of the forces at work in the galaxy. These hot, unforgiving stars remind us that every world, every potential abode for life, depends on a delicate, precarious balance between the relentless onslaught of stellar radiation, the steady pull of gravity, and the inherent strength and resilience of its own atmosphere, a cosmic tightrope walk. Among the rarest and most extreme objects in the galaxy are magnetars, a truly special and exotic type of neutron star. What sets them apart are their magnetic fields, which are far far stronger than anything found elsewhere in the known universe, billions of times more powerful than any magnet we can conceive of. These fields are so incredibly intense that they can actually distort the very structure of atoms and profoundly influence the surrounding space in unusual, almost unimaginable ways. Magnetars occasionally release sudden, incredibly powerful bursts of energy that can briefly outshine all other stars in their immediate vicinity, making them appear like cosmic flashes. These dramatic bursts originate from sudden, violent shifts in the magnetar's incredibly strong magnetic field, which can cause the star's rigid crust to crack and rupture. The resulting flare sends powerful, high-energy radiation surging into space, detectable across vast distances. Although magnetars are only a few kilometers across, incredibly compact, their influence can be felt over truly great cosmic distances. They rotate relatively slowly compared to other neutron stars, but their sheer magnetic power makes them utterly distinctive and unique. Studying magnetars helps astronomers understand how matter behaves under the most extreme conditions imaginable, pushing the boundaries of physics. The very existence of such objects adds a profound sense of mystery and awe to the Milky Way, showing that even among neutron stars, which are already extreme, there are rare and extraordinary members that defy easy categorization. Magnetars stand as powerful reminders that the galaxy hosts phenomena far beyond our ordinary experience, places where gravity, magnetism, and energy combine in dramatic, violent, and truly surprising ways, challenging our fundamental understanding of the cosmos. Across the vast, star-filled expanse of the Milky Way, there are planets that do not simply circle a single star, but instead move gracefully and complexly between two, locked in an intricate gravitational dance. These worlds orbit binary stars, following paths that are meticulously shaped by the combined, dual pull of both suns. Depending on the precise distance and separation between the two stars, a planet might either move around them together, as if they were a single, luminous center of gravity, or it might weave a more complex, figure eight, like orbit between them, constantly balancing the gravitational tugs. Sunrises and sunsets on such worlds would be unlike anything imaginable on Earth. Sometimes, both suns would rise simultaneously, painting the sky with double light. At other times, one sun might set dramatically as the other climbed into the sky, creating a never-ending, shifting spectacle of light and shadow. The climate on these planets can be incredibly unusual and complex, shaped by constant, dynamic changes in heat and light as they move through their intricate orbits. These binary systems reveal just how flexible and adaptable planetary formation can be. Instead of being disrupted or ejected by the presence of two powerful stars, the surrounding disk of gas and dust can still gather into planets that manage to find remarkably stable, albeit complex, orbital paths. Studying these fascinating systems helps astronomers understand how planets adapt to radically different stellar environments and how common these multi-star planetary arrangements might truly be across the galaxy. The profound idea that entire worlds orbit twin suns, experiencing a perpetual dual sunrise and sunset, adds a quiet, almost poetic sense of wonder to the Milky Way, showing us that nature often constructs more creative and diverse structures than we initially expect, constantly surprising us with its ingenuity. Deep within the very center of the Milky Way, cloaked in gas and dust, lie faint, but persistent traces of something incredibly rare and mysterious: antimatter. This exotic form of matter, which behaves as an opposite twin to normal particles, appears in diffuse, faint clouds within this incredibly energetic region. These antimatter clouds are not thick or bright, but their presence can be definitively detected through the specific radiation produced when antimatter meets normal matter and undergoes the dramatic process of annihilation, converting mass directly into energy. The precise origins of this antimatter are still an active area of scientific study. It may originate from the intense activity of massive stars, from energetic jets of particles ejected near the central supermassive black hole, or from complex interactions within the dense clouds of gas and dust that populate the core. Because antimatter is incredibly difficult to produce in nature and even harder to preserve as it annihilates upon contact with normal matter, its sustained presence in the galaxy, even in faint traces, is truly surprising and significant. Studying these enigmatic clouds helps scientists to learn about the high-energy processes occurring in the central region of our galaxy. It reveals extreme conditions that cannot be easily recreated on Earth, where intense gravity, powerful magnetic fields, and frequent stellar explosions combine to create unique physical environments. These subtle, invisible signals demonstrate that the center of the Milky Way is far from a quiet or placid place. Instead, it is a dynamic, turbulent realm where unusual forms of energy gather, offering crucial clues about the strange and powerful events that continually shape our galaxy's enigmatic core. Stretching across the immense tapestry of the Milky Way are long, delicate trails of stars that drift through space like ghostly, shimmering ribbons. These are known as tidal streams, and they are the haunting remains of smaller galaxies or globular clusters that ventured too close to our own massive system. Over millions of years, the relentless, powerful gravity of the Milky Way slowly but surely pulled them apart, scattering their constituent stars along their former orbital paths, gradually dissolving their original structure. Each stream, therefore, carries within it the spectral memory of a galaxy or cluster that once had its own distinct shape, identity, and structure. By meticulously studying their precise motions and their unique chemical compositions, astronomers can painstakingly trace the history of these lost companions, understanding their demise. Some of these streams curve gracefully high above the galactic plane, looping through the halo, while others flow quietly and almost invisibly through the more crowded spiral arms of the main disk. Their distinctive shapes reveal a crucial aspect of how the Milky Way grows and evolves. By steadily absorbing smaller galaxies and star clusters, accumulating their stars over eons. These streams also serve as invaluable tools for mapping the distribution of dark matter, that invisible, mysterious substance that permeates the galaxy. Their paths bend and distort in response to the unseen gravitational influence of these dark matter structures surrounding the galaxy. Tidal streams powerfully remind us that the Milky Way has a long active and often violent past filled with gravitational interactions. It has interacted with many of its neighbors, each encounter leaving behind a faint, yet beautifully preserved, stellar signature. These stellar remnants drift silently through the cosmic night, carrying stories older than Earth itself, silent witnesses to galactic evolution. In many parts of the Milky Way, stars often form in pairs rather than in solitary isolation. These binary stars circle each other in an intricate, gravitational dance that can last for billions of years, a celestial pas de deux. Over immense stretches of time, however, some of these pairs slowly spiral inward, their orbits gradually shrinking as they exchange energy through various mechanisms, tidal forces, powerful stellar winds, or complex interactions with surrounding interstellar material. Eventually, after eons of this slow, inexorable inward spiral, the stars can grow close enough to one another to merge. This spectacular collision produces an enormous, cataclysmic burst of light and energy, sometimes creating a brief but incredibly spectacular event known as a luminous red nova, temporarily outshining many other stars. The newly merged star often becomes significantly larger and brighter than either of its predecessors, a cosmic phoenix. Binary collisions play a crucial role in enriching the galaxy with heavy elements, as material is intensely mixed and heated during the violent merger process, leading to new nucleosynthesis. Studying these dramatic unions helps astronomers understand how stars evolve under extreme conditions and how certain rare, exotic objects are formed in the galaxy. Although this process of stellar merging takes an immense amount of time, spanning millions to billions of years, the profound idea that two stars can slowly, gracefully fall toward one another until they become one adds a poetic sense of motion and transformation to the Milky Way. Even in the calm, serene night sky, quiet celestial dances are constantly unfolding in ways we can only begin to imagine, a testament to the dynamic nature of the cosmos. Among the thousands of worlds swirling within the Milky Way, some experience forms of weather so extreme and alien that they are entirely unlike anything found on Earth. On certain exceptionally hot exoplanets, where temperatures soar to unimaginable levels, metals like iron or titanium can evaporate into vapor, filling their atmospheres. When the atmosphere cools slightly, perhaps on the planet's night side or at higher altitudes, these metallic vapors condense into liquid droplets that fall as shimmering, metallic rain, coating the landscape in liquid metal. On other incredibly exotic worlds, powerful winds whip molten droplets of silicate rock across the sky, creating perpetual storms of molten glass that streak sideways at tremendous, hypersonic speeds. The surfaces of such planets can be glowing, turbulent oceans of lava, constantly reshaped and churned by violent, infernal heat. These extreme conditions typically occur on worlds that orbit incredibly close to their parent stars, receiving immense amounts of radiation, or those with highly unusual chemical compositions. Their atmospheres reflect the intense radiation they receive, leading to bizarre weather patterns shaped by forces utterly unknown on Earth. Observing these exotic and dangerous climates helps astronomers understand the astonishing diversity of environments that planets can host. Pushing the boundaries of our understanding, it reveals that weather in the galaxy is not limited to gentle clouds and storms of water, but can include conditions that feel truly otherworldly, like something out of a science fiction novel. These metal and glass rains transform distant planets into shimmering, dangerous, yet captivating landscapes, perpetually forged by unimaginable heat and alien winds, a testament to the universe's boundless creativity. Throughout the sprawling Milky Way, massive stars reach the dramatic ends of their lives in powerful, cataclysmic explosions, sending colossal shock waves rippling into the surrounding space. When many such explosions, perhaps from a cluster of massive stars, occur in the same general region over millions of years, their combined, synergistic energy can carve out enormous, truly vast cavities within the interstellar medium. These cavities contain far less gas and dust than the surrounding areas, appearing as colossal bubbles in the interstellar medium, meticulously shaped by overlapping shock fronts. Inside these hollowed-out spaces, the gas is often incredibly hot and thin, a rarefied plasma, while the edges of the cavities form denser, cooler walls where material has been swept aside and compressed. These grand structures reveal the rich history of star formation in their respective regions. Groups of massive stars tend to form together, live relatively short, brilliant lives, and then explode within a comparatively short span of cosmic time. Their collective, powerful activity profoundly reshapes the local environment, influencing where new stars will subsequently appear, acting as a cosmic feedback mechanism. Studying these immense cavities helps astronomers understand how energy, released from dying stars, moves and propagates through the galaxy, acting as a powerful sculptor. It vividly shows that the Milky Way is continually shaped by ongoing cycles of stellar birth and destruction, each dramatic event leaving its indelible mark in the form of these vast, hollowed-out regions, a testament to the galaxy's dynamic, ever-changing nature. Not all stars remain peacefully within the boundaries of the galaxies where they were born. Some, in a dramatic and violent turn of events, are forcefully ejected during powerful gravitational interactions, becoming cosmic exiles. When a star passes perilously close to a supermassive black hole, or a tightly bound, dense star cluster, it can gain enough kinetic energy and speed to completely escape the gravitational pull of its home galaxy, becoming an intergalactic wanderer. Once thrown free, it embarks on a lonely, solitary journey, drifting through the immense, dark void of intergalactic space, far from any galactic home. These stars continue to shine just like any other, powered by their internal fusion. But their profound isolation makes them incredibly difficult to detect. As they lack the luminous backdrop of a galaxy, their journeys may take them incredibly far from any source of light or warmth, traversing the silent, cold spaces between galaxies for billions of years. The Milky Way has likely ejected many such stars over its long, tumultuous history. Some were violently launched during past collisions with other galaxies, while others were cast away when their binary companions exploded in supernova, abruptly altering the gravitational balance of their system. Studying these runaway intergalactic stars helps astronomers understand the extreme events that can occur in galactic environments, pushing the boundaries of gravitational dynamics. They serve as poignant reminders that the universe is a place of constant motion and profound change, where even stars, those symbols of stability, can be cast adrift into the cosmic ocean. These solitary wanderers drift through the deep dark, carrying the silent story of the violent events that set them free, eternal nomads in the vastness. Scattered throughout the Milky Way, like ancient, glittering pearls, are globular clusters, dense, spherical collections of millions of stars that formed in the very earliest epochs, when our galaxy was still young and coalescing. Many of these venerable clusters are significantly older than Earth itself, older than our Sun, and indeed, older than the planets in every known solar system. They contain some of the very first generations of stars created in the universe, formed long before the galaxy settled into its current, graceful spiral shape. The stars within these clusters move in incredibly tight, intricately packed orbits, so closely gathered that if viewed from within, the night sky would be entirely filled with a dazzling, continuous tapestry of light, unlike anything we can imagine. Their unique chemistry, characterized by a very low abundance of heavy elements, reveals what the early universe was like in its nascent stages, long before heavier elements, forged in supernovae, became common. These clusters orbit far outside the main disk of the Milky Way, drifting through the expansive galactic halo on long, looping paths like ancient sentinels. Observing them helps scientists to meticulously reconstruct the deep history of the galaxy and understand how its earliest, most fundamental structures formed. Their incredible age bestows upon them a quiet dignity. They have silently survived countless collisions, mergers, and innumerable cosmic events over billions of years. They are truly ancient survivors, floating serenely through a galaxy that has dramatically changed and evolved since they first ignited their light, billions of years ago, silent witnesses to cosmic history. There are stars in our galaxy, known as pulsars, that rotate with astonishing speed and emit focused beams of radiation from their powerful magnetic poles. As these cosmic lighthouses spin, their beams sweep across space, much like the rotating beacon of a terrestrial lighthouse. When one of these beams points directly toward Earth, even for a fleeting moment, we detect a precise, rhythmic pulse of light that repeats with remarkable, almost clock-like precision. The effect is indeed similar to a lighthouse turning in the night, though the power and scale are infinitely grander. Pulsars are created when massive stars, after exhausting their nuclear fuel, collapse catastrophically into incredibly dense neutron stars following a supernova explosion. Their incredibly rapid rotation and intense magnetic fields make them truly unique among stellar remnants. Some pulsars spin several times per second, while others rotate hundreds of times in that incredibly short span, a dizzying cosmic ballet. Their steady, precise pulses are invaluable tools for astronomers, helping them to accurately measure cosmic distances, map distant regions of the galaxy, and even study fundamental physics under extreme conditions. Pulsars reveal how matter behaves when compressed to densities almost beyond comprehension. They also contribute significantly to our understanding of gravitational waves, as pairs of pulsars orbiting each other can produce detectable ripples in spacetime, a prediction of Einstein's theory of general relativity. These cosmic lighthouses add a profound rhythm to the Milky Way, sending steady, unwavering signals through the darkness that allow us to study far-off regions with surprising clarity and precision, extending our senses across the vastness. Throughout the Milky Way, there are specific zones that emit a faint, yet persistent, radiation, a lingering glow from past cataclysms. This pervasive glow represents the leftover energy from ancient, incredibly powerful events, such as supernovae explosions, gamma-ray bursts, or complex interactions between dense clouds of gas and high-energy particles. These regions may no longer contain the original sources of the disturbance. The stars or objects that caused them may have long since vanished or transformed. Yet, the radiation remains, a lingering signature of intense past activity, a cosmic echo. The glow often appears in wavelengths invisible to human eyes, such as X-rays or gamma rays, requiring specialized instruments for detection. Observing these radiating regions allows astronomers to uncover the hidden, violent history of the galaxy, like cosmic archaeologists. They reveal areas where powerful, transformative events once occurred, profoundly shaping the surrounding environment and distributing heavy elements. Some of this radiation originates from electrons spiraling rapidly through strong magnetic fields, while other portions come from gas heated to extraordinary incandescent temperatures. These glowing zones serve as powerful reminders that the galaxy has experienced many energetic episodes throughout its long history. Even though the original explosions or events may have happened long before human beings existed, their echoes still travel through space, patiently telling their stories. This quiet, pervasive radiation tells silent stories of enormous, powerful forces that once stirred the Milky Way, leaving behind subtle traces that can linger for millions of years, a profound testament to the galaxy's dynamic past. Near the very heart of the Milky Way, incredibly close to the central supermassive black hole, clouds of gas behave in ways that seem almost unreal, defying our everyday intuition. These clouds orbit in close proximity to the central black hole, where gravity becomes unbelievably strong and warping. As a direct result, they move with speeds that are truly difficult to imagine, velocities that would utterly shatter any terrestrial understanding of motion. Some of these clouds race around the galactic center at hundreds of kilometers per second, tracing elongated, highly eccentric loops shaped by the uneven distribution of immense mass in that extreme region. The environment here is incredibly dense with intense radiation, powerful magnetic fields, and countless swirling stars, creating a chaotic, turbulent maelstrom. These factors create immense turbulence that twists and stretches the gas clouds into strange, contorted shapes, constantly reshaping them. Observing them requires sophisticated infrared and radio telescopes because thick, obscuring layers of dust completely block any visible light from reaching us. When scientists meticulously track their movement, they observe gas rushing, colliding violently, and flowing in intricate spirals that reveal the invisible gravitational structure of the core. These rapid, almost incomprehensible motions also help astronomers to accurately estimate the colossal mass of the central black hole by showing how strongly the entire region pulls on its surroundings, acting as a gravitational anchor. The incredible pace and raw energy of this central environment contrast sharply with the calm, serene appearance of the night sky we observe from Earth. Deep inside the Milky Way, these gas clouds dance at unimaginable speeds, shaped by forces far, far stronger and more dynamic than anything found near our quiet, distant Earth. Not all planets follow slow, majestic, sweeping orbits like the ones we are familiar with in our own solar system. In the vast, diverse expanse of the Milky Way, there are worlds that circle their stars so incredibly closely that they complete an entire orbit in a matter of mere minutes, rather than years. These ultra-short period planets hug their parent stars so tightly that the side, perpetually facing the star, becomes incredibly hot, a scorching inferno, while the far side remains much cooler, perhaps even frozen. Their orbital paths are shaped by intense, unrelenting gravity and fierce, continuous radiation that constantly pulls at and erodes their atmospheres. Many of these extreme worlds may have lost much of their original material, their outer layers stripped away by stellar winds, leaving behind dense, exposed rocky cores. Their extreme proximity to their stars means that they move at extraordinary orbital speeds, sometimes traveling tens of kilometers each second, a dizzying pace. Studying these unique planets helps scientists understand how worlds evolve under truly extreme conditions, pushing the boundaries of planetary physics. They reveal how orbits can shrink over time due to various forces and how planets adapt, or fail to adapt, to intense, continuous heat. These rapid orbits also create unusual, extremely short cycles of day and night, where a year might last only a few minutes. The very idea of a year lasting only a few minutes challenges our fundamental sense of planetary motion and highlights the incredible, almost boundless variety of stellar and planetary systems that exist throughout the galaxy. The Milky Way is a testament to the universe's boundless creativity in forging celestial bodies. Among the myriad worlds in our galaxy, some are believed to be almost entirely dominated by water, but in forms not typically found on Earth. These ocean planets contain vast quantities of water, not just as liquid, but also as exotic, high-pressure ices and superheated liquids that behave very differently from anything familiar to us. They may possess incredibly thick atmospheres that efficiently trap heat, creating deep, layered oceans of superheated water far beneath their perpetual clouds. Under the intense pressures found deep within these worlds, water can transform into exotic states, forming dense, crystalline structures of ice that are utterly alien to our experience. These planets are often larger than Earth, with strong gravitational fields that hold their deep, immense oceans in place. Some may even have rocky cores buried beneath hundreds of kilometers of water, an inverted world. Observing them helps astronomers understand how planets form from different initial materials and under a wide range of temperatures. Their existence expands our idea of what a habitable world might look like, challenging our Earth-centric biases. Instead of continents and oceans, these worlds could be global seas, with no exposed land whatsoever. Imagining entire planets shaped and dominated by water, yet entirely unlike Earth in their composition and internal structure, brings a profound sense of quiet wonder to the Milky Way. They powerfully remind us that planetary diversity is far greater and more surprising than we once believed, pushing the boundaries of our cosmic imagination. Not every star in the Milky Way burns with fierce, incandescent heat, blazing brightly across the light years. Some stars are so incredibly cool and faint that their surface temperatures barely exceed those of giant planets, blurring the traditional distinction between star and planet. These ultracool dwarfs emit most of their light in infrared wavelengths, making them nearly invisible to the unaided human eye, glowing softly in the heat spectrum. Despite their small size and dimness, they are still true stars, powered by the steady, patient nuclear fusion of hydrogen deep within their cores, albeit at a much slower rate. Their extremely low temperatures allow complex molecules to form and persist in their atmospheres, creating intricate patterns of light absorption that astronomers can detect. Studying these stars helps astronomers understand the lower limits of stellar formation, how small and cool a body can be, and still be considered a true star. They also provide valuable clues about how gas giant planets might appear when viewed from a distance, offering a comparative perspective. Some of these cool stars host their own planetary systems, where temperatures are gentle enough to potentially allow for a wide range of conditions, perhaps even supporting life. Because they shine so softly, life on planets orbiting them would experience a perpetually dim and reddish world, bathed in a gentle, ruddy glow. These cool stars remind us that the Milky Way contains many diverse forms of starlight, from blazing, massive giants to quiet, ember, like suns that subtly blur the line between what we define as a star and what we define as a planet, expanding our cosmic lexicon. Threaded throughout the Milky Way are immense, ethereal arcs of gas that span truly incredible distances, light years in length. These graceful arcs are shaped by a dynamic mix of powerful stellar winds from massive stars, the shock waves from cataclysmic supernova explosions, and the subtle yet pervasive influence of magnetic forces that continuously push and pull the gas over vast periods. Some arcs form curved, luminous walls around old, cleared-out cavities in the interstellar medium, remnants of past stellar activity. Others trace long, sweeping paths created by the relentless motion of massive stars as they plow through the diffuse interstellar medium, leaving a wake of compressed gas. Because the gas within these arcs is often incredibly thin and cold, it can be extremely difficult to detect in visible light. However, radio and infrared telescopes can reveal their intricate structure, showing delicate curves that stretch across hundreds of trillions of kilometers, a testament to the immense scale of these cosmic brushstrokes. These arcs help astronomers decipher the history of star formation in their respective regions. Their shapes reveal the remnants of past explosions, the intricate flow of energy through the galaxy, and the nuanced ways in which gas clouds respond to the omnipresent forces of gravity and pressure. They act like enormous, silent cosmic brushstrokes, vividly marking areas where powerful forces once swept through, leaving an indelible imprint. Seeing these graceful shapes mapped across the Milky Way adds a profound sense of artistry to the galaxy, as if vast, unseen hands had shaped its diffuse gas into beautiful, curved forms, a celestial sculpture. Throughout the galaxy, groups of stars travel in serene harmony across truly great distances, moving together as if engaged in an eternal, slow motion ballet. These drifting clusters form when stars are born simultaneously within a single, massive cloud of gas and dust. Over immense periods of time, gravitational interactions with other stars and passing gas clouds gently, slowly pull the cluster apart, gradually dispersing its members. Yet, many of these stars continue moving in the same general direction, preserving a collective memory of their shared origin. These moving groups can persist for hundreds of millions of years, maintaining remarkably similar speeds and positions even as they slowly spread out, becoming more diffuse. Because the stars within these groups share a common birthplace, they often have similar chemical compositions and ages, providing invaluable clues for astronomers. Studying these moving groups helps scientists trace the history of star formation and understand how stellar clusters gradually dissolve over time, fading into the general galactic population. They also reveal how stars migrate through the galaxy, drifting from their birthplaces into entirely new regions of space, altering the local stellar demographics. Some moving groups eventually become so spread out that they blend almost imperceptibly into the background population of the Milky Way, their shared origin lost to casual observation. Others, however, remain coherent for long stretches, like quiet caravans traveling across the galactic landscape, their shared journey a testament to their enduring gravitational bonds. Their gentle, synchronized motion adds a sense of continuity to the Milky Way, showing how stars carry their shared beginnings with them, a subtle, cosmic heritage, as they drift silently through the vastness. Certain stars in the galaxy produce incredibly narrow, powerful jets of particles that shoot outward into space at tremendous, almost unimaginable speeds. These dramatic jets often form when material spirals onto a dense object, such as a neutron star or a young, nascent star still surrounded by a swirling disk of gas and dust. As the material inexorably falls inward toward the central object, powerful magnetic fields twist and focus it into slender, collimated streams that leap into space, accelerating to relativistic velocities. These jets can travel for truly long distances, sometimes reaching light years from their source, powerfully illuminating the surrounding gas and carving intricate paths that reveal the underlying structure of the region. In the case of young stars, these jets play a crucial role by helping to clear away the leftover material from the formation process, allowing the star to fully emerge. In older, more compact stars, the jets can become extremely energetic, producing high-energy radiation detectable across the galaxy, acting as cosmic beacons. These dramatic phenomena vividly demonstrate how magnetic fields and gravity combine to create powerful, elegant, and often violent structures in the cosmos. The sight of a star launching focused, luminous streams of energy into the dark expanse is a profound reminder of how dynamic and creative the universe can be, even on seemingly small scales. Even relatively small stellar systems can produce effects that reach far beyond their immediate surroundings, profoundly influencing vast regions of space around them. Most stars in the Milky Way follow stable, predictable orbits, meticulously shaped by the galaxy's immense, distributed mass. However, a rare and fascinating group of stars travels at truly extraordinary speeds, velocities so immense that they are fast enough to eventually leave the Milky Way entirely, escaping its gravitational embrace forever. These hypervelocity stars are launched into these incredible trajectories by incredibly powerful gravitational interactions. Some are violently slingshotted by the central supermassive black hole when they pass too perilously close, gaining immense momentum. Others are released when their binary partners explode in a supernova, abruptly freeing them from their orbital dance and sending them hurtling outward. Once dramatically accelerated, these stars move on long, hyperbolic paths continuously outward, eventually drifting into the cold, dark expanse of intergalactic space, becoming truly isolated. They continue to shine like ordinary stars, but their unusual, extreme velocities clearly reveal their dramatic and violent histories. Studying them helps astronomers understand the extreme conditions near the galactic center and the dramatic, often chaotic, outcomes of supernova explosions. These runaway stars serve as a poignant reminder that even massive galaxies, with their immense gravitational pull, cannot hold all their members forever. Some, by chance or by violent interaction, will break free, carrying their light into the empty, silent space between galaxies. Their journeys will last for billions of years, silent and solitary, shaped forever by the singular, powerful moment that set them on their way, a testament to cosmic freedom. Scattered throughout the galaxy are clouds composed not of cold, neutral gas, but of energized plasma, a fourth state of matter. These regions contain charged particles, ions and free electrons, that respond strongly and dynamically to magnetic fields. As a result, they behave very differently from ordinary gas clouds. They can twist into intricate filaments, ripple like waves across vast distances, or glow with a soft, ethereal light generated by electrons spiraling through complex magnetic structures. Many of these plasma clouds are created by massive, hot stars or cataclysmic supernova explosions that continuously pump immense amounts of energy into their surroundings. Others are shaped by turbulence within the interstellar medium, a constant churning of gas and fields. Studying these regions provides invaluable insight into the invisible, yet pervasive, magnetic environment of the Milky Way, which cannot be observed directly. Plasma clouds help astronomers to trace the hidden magnetic fields that thread through and permeate the entire galaxy, acting as invisible guides. They also profoundly influence how cosmic rays travel, guiding or deflecting them as they move through space, altering their trajectories. These charged regions add another intricate layer of complexity to the Milky Way, revealing that the spaces between stars are not truly empty, but are filled with subtle, dynamic energy, meticulously shaped by both matter and powerful magnetic forces, an unseen cosmic web. Throughout the Milky Way, there are vast, breathtaking nebulae, colossal clouds of gas and dust, brilliantly lit by the presence of young, incredibly massive stars. These stars emit intense ultraviolet light that energizes the surrounding gas, causing it to glow with vivid, almost otherworldly colors. Hydrogen, the most abundant element, typically glows in soft, ethereal reds, while oxygen can produce gentle greens or striking blues, creating a celestial palette. These glowing clouds are often the very birthplaces of new stars, acting as stellar nurseries. Inside them, dense pockets of gas slowly collapse into young, nascent suns that eventually emerge from the surrounding material, dispersing the dust. The intricate, often fantastical shapes of these nebulae are sculpted by powerful stellar winds, relentless radiation pressure, and cosmic turbulence, forming arches, towering pillars, and vast, hollowed-out cavities that create some of the most striking and beautiful scenes in the entire galaxy. Studying these nebulae helps astronomers understand how stars form, from their initial collapse to their emergence, and how they profoundly influence their immediate environment. The glowing clouds also reveal the precise chemical makeup of the galaxy, as different elements, when energized, produce distinct colors. These luminous regions, therefore, serve as a constant reminder that star birth is both a powerful and a deeply beautiful process, a cosmic act of creation. They fill the Milky Way with soft, colorful light, transforming ordinary, diffuse gas into radiant, intricate sculptures, meticulously shaped by the omnipresent energy and light of young and incredibly energetic stars, a masterpiece of cosmic artistry. Brown dwarfs fill a quiet, enigmatic space between planets and stars, blurring the traditional definitions. They form when clouds of gas collapse, much as they would during star formation, but the resulting object never gathers enough mass, specifically, about 8% of the Sun's mass, to ignite sustained nuclear fusion of ordinary hydrogen in its core. Without this steady, powerful source of internal energy, brown dwarfs shine only faintly, glowing softly with the residual heat left over from their gravitational formation, a gentle, fading ember. They can have masses far greater than even the largest planets, yet remain too cool and dim to appear as true stars. Because their light is inherently weak and predominantly emitted in infrared wavelengths, many brown dwarfs remain unseen, drifting quietly and mysteriously through the Milky Way, cosmic phantoms. These elusive objects help astronomers understand the lower limits of star formation, defining the boundary between stars and planets. Their atmospheres contain unusual molecules, such as methane and water vapor, shaped by their cool temperatures and relatively high pressures, providing unique spectral signatures. Some brown dwarfs even exhibit dynamic weather patterns that shift over hours or days, revealing turbulent behavior in their cloud layers, much like gas giant planets. Although they do not burn like true stars, they play an important role in the galaxy's population, filling the vast spaces between bright stars and adding a hidden complexity to the Milky Way's demographics. Their gentle, fading glow and mysterious nature offer a profound reminder that not all celestial bodies fit neatly into familiar categories, constantly challenging our classifications. Among the thousands of worlds in the Milky Way, certain exoplanets orbit so incredibly close to their parent stars that their surfaces melt into glowing, turbulent seas of molten rock. These lava worlds are perpetually shaped by intense, unyielding heat that prevents any solid crust from forming or stabilizing for long. Instead, their surfaces churn with rivers of liquid stone, slowly flowing under the relentless pull of gravity and the powerful motion of their atmospheric winds, creating an infernal landscape. The temperatures on these planets can exceed the melting points of many common minerals, turning their entire landscapes into luminous, fiery red and orange vistas, a truly hellish sight. Some of these worlds also experience powerful tidal forces from their host stars, which generate immense internal friction and heat, causing their interiors to become even hotter. As a result, volcanic activity can become widespread and continuous, feeding the lava oceans that constantly renew themselves, a perpetual cycle of destruction and creation. Studying these extreme planets helps astronomers understand how worlds evolve under conditions of extreme radiation and tidal stress. Their atmospheres can even contain vaporized rock, which then condenses into mineral clouds. When these clouds cool at higher altitudes, they can produce unusual forms of precipitation that fall back into the molten surface, creating a truly alien hydrological cycle. Lava worlds demonstrate that planetary environments in the galaxy vary far beyond anything seen on Earth, offering a glimpse into cosmic landscapes forged by intense heat and relentless motion in the harshest possible conditions, a testament to the universe's extremes. Pulsars in the Milky Way are rapidly rotating neutron stars that send out focused beams of radiation from their magnetic poles. Each time one of these beams sweeps past Earth, it produces a pulse of light that arrives with remarkable, almost unparalleled regularity and precision. Some pulsars maintain a timing so incredibly consistent that they rival atomic clocks in their stability, making them among the most precise timekeepers in the universe. This extraordinary precision makes them invaluable tools for studying the galaxy and fundamental physics. By meticulously observing slight changes in the pulse timing, astronomers can detect the subtle influence of passing objects, the elusive ripples of gravitational waves, or even internal movements within the pulsar itself. The rapid rotation of a pulsar is a relic of the massive star that created it. When a massive star collapses into a neutron star, its core shrinks dramatically, causing it to spin much faster, in the same way that a spinning ice skater speeds up when they draw in their arms. Although pulsars gradually slow down over millions of years as they radiate energy, their early stages can feature hundreds of rotations each second, a dizzying rate. Their intense magnetic fields guide charged particles along narrow paths, creating the powerful beams that make them so distinctive. Pulsars serve as natural laboratories for extreme physics, revealing how matter behaves under conditions far beyond any experiment possible on Earth, pushing the boundaries of our understanding of matter. Deep within the central regions of the Milky Way lies an enormous, yet largely hidden, reservoir of molecular gas. This material is dense, incredibly cold, and extraordinarily rich in the pristine ingredients needed for active star formation. However, the center of the galaxy is far from a quiet or simple place. Strong radiation fields from massive stars and the central black hole turbulent motions, and intense gravity constantly affect this gas, shaping its behavior. Clouds are stretched, compressed, and heated as they orbit in close proximity to the central supermassive black hole, creating a dynamic, chaotic environment. Despite these harsh conditions, pockets of gas remain shielded enough for complex molecules to survive and even thrive. These regions form some of the most massive and active star-forming sites in the entire galaxy, continually replenishing the stellar population of the core. Observing them requires using radio and infrared wavelengths of light, which can penetrate the thick, obscuring dust surrounding the core, revealing its secrets. The distribution and dynamics of this molecular gas help astronomers understand how stars form under extreme conditions where gas is constantly being agitated and compressed. It also reveals how energy moves through the galactic center, profoundly shaping the evolution of nearby regions. These hidden stores of gas play a crucial role in building new generations of stars, showing that even the most intense and seemingly hostile environments can be fertile grounds for creation, a testament to the resilience of cosmic processes. Not all planets revolve around stars alone. In rare and fascinating cases, two planets of similar mass form close enough to one another that they share a mutual orbit, bound together like cosmic dance partners. Instead of one planet dominating the other, the pair circles a common center of gravity, known as the barycenter, which is located somewhere between them. These double-planet systems move through space like partners performing a slow, graceful, and perpetual waltz. Their shared motion profoundly affects their individual rotations, their internal tides, and their long-term stability, creating a complex, interconnected system. Finding such systems is incredibly challenging because, when viewed from afar, they often resemble a single, more massive planet. However, detailed observations can reveal subtle variations in their orbits that hint at their dual nature, requiring meticulous study. These systems provide invaluable insight into how planets form and interact in complex gravitational environments. They show that worlds can develop in cooperative pairs rather than strictly solitary paths, expanding our understanding of planetary genesis. The existence of such intricate arrangements highlights the astonishing diversity of planetary configurations possible in the Milky Way. Imagining two planets, eternally bound together in a cosmic waltz, adds a touch of elegance and romanticism to the vast and varied structures scattered across the galaxy, a beautiful display of celestial mechanics. Certain stars rotate so incredibly quickly that they become noticeably flattened, their perfect spherical shape dramatically distorted. Their equators bulge outward due to the powerful centrifugal force generated by their rapid spin, while their poles remain more compact and compressed. This distinct, oblate shape profoundly affects the distribution of temperature across their surface. The poles tend to be hotter and brighter because the material there is more compressed and closer to the star's core, while the equator, distended and cooler, can appear dimmer. This phenomenon is scientifically known as gravity darkening. Rapidly rotating stars are often young and massive, still retaining much of the angular momentum from their formation process. Their rotation also significantly influences how they evolve over their lifetimes. Fast, spinning stars can mix their internal layers more efficiently, altering the way they burn their nuclear fuel and thus affecting their lifespan and luminosity. Observing these stars helps astronomers understand the complex interactions between rotation, internal structure, and energy output, pushing the boundaries of stellar physics. Their distorted shapes challenge the simplistic idea of stars as perfect, serene spheres. They reveal that even familiar, looking points of light can hide unusual and dramatic physical behavior. These flattened stars add another level of diversity to the Milky Way, showing that the force of rotation can sculpt a star into forms very different from the more perfectly spherical ones we see near our home, a testament to the dynamic forces at play. When a massive star explodes, it leaves behind a colossal, expanding cloud of gas and debris known as a supernova remnant. These remnants continue to expand outward for thousands of years, interacting dynamically with the surrounding interstellar medium. Even long after the initial, brilliant explosion has faded from visible view, the remnants continue to glow, a lingering testament to the star's violent demise. Powerful shock waves within the remnant heat the gas to incredibly high temperatures, producing X-rays and visible light that can be observed for millennia. The intricate filaments and knots within the remnant reveal crucial details about the original star, its mass, and the immense force of the explosion. Studying these remnants helps astronomers understand how heavy elements, forged in the heart of massive stars and during the explosion itself, are dispersed throughout the Milky Way, enriching the galaxy. They also vividly demonstrate how the immense energy from dying stars profoundly shapes nearby regions, carving out cavities and triggering new star formation. Over time, the expanding remnant slows and cools, eventually blending into the surrounding gas and dust, its distinct identity fading. Yet, during its active phase, it stands as a brilliant, powerful reminder of the dramatic, transformative events that occur when massive stars reach the ends of their luminous lives. These glowing clouds show that the aftermath of a supernova remains vibrant and full of scientific information long after the initial flash has faded, a cosmic echo that resonates through time. In the Milky Way, there are planets that orbit so incredibly close to their parent stars that their surfaces heat to extreme, incandescent temperatures. These hot Jupiters, or lava planets, are often large and gaseous, with atmospheres that swell and shimmer under the intense, relentless radiation from their nearby star. The extreme heat causes their upper clouds to glow, sometimes giving the entire planet a reddish or golden hue, a permanent, fairy sunset. Their dayside temperatures can vaporize minerals and metals, creating exotic and bizarre atmospheric chemistry, far removed from anything we see on Earth. The intense stellar winds from their host stars constantly strip away particles from their upper atmospheric layers, forming long, trailing tails of gas that stream behind them like comets. These planets complete their orbits incredibly quickly, sometimes in only a few Earth days, a dizzying pace. Studying them reveals how planets adapt, or fail to adapt, to being in such harsh, close proximity to their stars. Their unique structure, extreme weather patterns, and the processes of atmospheric escape provide valuable clues about planetary survival under truly extreme conditions. These red, hot worlds show that the Milky Way contains planets far stranger and more varied than the ones found in our own solar system, pushing the boundaries of our planetary imagination. In the coldest, most sheltered regions of the galaxy, far from the intense heat and light of active star formation, clouds of gas can become so incredibly cold that molecules begin to freeze onto the surfaces of tiny dust grains. These frozen coatings form delicate ice crystals, composed of common compounds like water, carbon dioxide, methane, and other more complex molecules. These ice crystals play an incredibly important role in the complex chemistry of the interstellar medium. They provide crucial surfaces where more complex molecules can form through surface reactions, gradually building the raw materials that may one day contribute to the formation of new planets, comets, or even the precursors to life itself. Infrared observations are essential for revealing the presence of these interstellar ices, as they exhibit distinctive absorption patterns at specific wavelengths. These frozen clouds, being opaque to visible light, hide their chemical treasures behind thick veils of dust, making them appear as dark, empty regions. Studying them helps astronomers understand the earliest stages of star and planet formation, providing insights into the chemical processes that occur before a solar system fully forms. They show how cold and quiet the galaxy can become in its most sheltered corners, a realm of profound stillness. These icy environments act as gentle, cosmic incubators, where complex chemistry slowly unfolds over millions of years, laying the groundwork for future creation. Red giants represent a dramatic, late stage in the life cycle of many stars, including what our Sun will eventually become. As these stars exhaust the primary hydrogen fuel in their cores, they undergo profound internal changes, causing them to expand dramatically and cool, becoming vast and incredibly luminous, often appearing reddish in color. Inside these vast, distended envelopes, new elements are forged through a series of nuclear reactions, as heavier elements are created from lighter ones. Over time, red giants gently, but persistently, shed their outer layers, releasing these newly forged elements into the interstellar medium, enriching the cosmic soup. This material, now infused with heavier elements, becomes part of the gas and dust that will eventually coalesce to form new generations of stars and planets. In this profound way, red giants continually enrich the galaxy with the essential building blocks for future generations of celestial bodies, acting as cosmic recyclers. Their slow, steady stellar winds carry carbon, nitrogen, oxygen, and other essential elements far into space, dispersing them widely. Observing red giants helps scientists understand the chemical evolution of the Milky Way, tracing the cosmic journey of elements. Their gentle, pervasive glow and constant contribution to the cosmic cycle add a sense of deep continuity and interconnectedness to the galaxy. They remind us that creation and renewal are intricately woven into the very life of every star, even those nearing the end of their luminous journey, their dying breaths fueling new beginnings. Not all stars follow neat, circular, or even modestly elliptical paths around the Milky Way's center. Some move on incredibly long, stretched-out orbits that carry them from one side of the galaxy to the other, traversing immense distances. These wandering stars travel through regions with wildly different densities of gas, radiation, and gravitational pull, experiencing a diverse range of galactic environments. Their elongated paths often originate when the stars were born in smaller, satellite galaxies that were later absorbed and consumed by the much larger Milky Way. As these smaller galaxies broke apart under the Milky Way's tidal forces, their stars were captured and set on these wide, ranging, eccentric orbits. Other stars may have been violently thrown into these eccentric paths by close encounters with massive objects, such as other stars, black holes, or dense star clusters. Their incredible journeys take them far above the galactic plane, then back down through the crowded spiral arms, a cosmic roller coaster. Observing these intrepid travelers allows astronomers to study the intricate structure and immense mass of the galaxy on truly large scales. Their motions reveal how the Milky Way's gravitational field changes and varies from one region to another, providing a dynamic map of galactic mass. These wandering stars act as quiet, ancient messengers from the galaxy's deep past, carrying evidence of long, vanished mergers and ancient gravitational interactions. Their wide, looping orbits show that the Milky Way is not a static, unchanging disk, but a dynamic, ever-evolving system, perpetually shaped by countless events and interactions over billions of years, a living, breathing entity. Surrounding the bright, familiar disk of the Milky Way is a vast, ethereal halo filled with extremely old and faint stars. These stars drift through space with slow, steady motion, far removed from the bustling, vibrant regions where new stars are actively being born. Many of them formed in the earliest eras of the galaxy's history, billions of years ago, before the iconic spiral arms even began to take shape. Their incredibly low brightness makes them challenging to detect, and their wide, diffuse distribution means they are separated by truly great distances, making the halo a sparse, lonely place. These halo stars often have unusual chemical compositions containing very small amounts of heavy elements, a telltale sign of their ancient origins. Studying them helps astronomers understand the conditions that existed shortly after the universe began forming its very first stars, providing a window into cosmic dawn. Some halo stars belong to ancient globular clusters that have survived for billions of years, while others were once part of smaller satellite galaxies that eventually merged with the Milky Way, their identity now lost. Because the halo is so sparse, its stars appear isolated, shining quietly against the deep, dark background of space, like cosmic ghosts. These drifting lights remind us of the Milky Way's earliest chapters, still present and shining, even after the galaxy has changed dramatically and evolved over immense periods of time, a silent testament to its origins. In some binary star systems, a planet can settle into a remarkably stable orbit that places it precisely between two stars, maintaining a balanced, delicate configuration. When this rare celestial alignment occurs, the combined light from the pair of stars can create a world perpetually bathed in constant twilight. The sky on such a world would never become fully dark, and true, blazing day might never quite arrive. The lighting on these worlds would shift softly and subtly as the stars move in their own intricate orbits. But profound darkness would remain an extremely rare, fleeting occurrence. Temperatures on these unique planets depend critically on their precise distance from both stars and the combined intensity of their light. Some of these twilight worlds may maintain mild, temperate conditions, while others could be perpetually cold or even warm enough to allow liquid water to exist on their surfaces. The gravitational forces from two stars create complex and intricate patterns in the planet's orbit. Yet many of these configurations can remain remarkably stable for long periods, defying initial expectations of chaos. Studying such systems shows how planetary environments can vary in truly surprising and unexpected ways. They reveal that sunlight is not always simple or singular, but can be a complex, dual illumination. These dusk-lit worlds offer a mesmerizing picture of planetary life shaped by a soft, constant, and perhaps perpetual glow, a unique cosmic experience. Deep within the Milky Way lie vast regions of cold gas and dust, often known as stellar nurseries, where new stars are actively being born. These vibrant regions often produce not just single stars, but entire clusters of them, a simultaneous burst of creation. As gravity pulls large quantities of gas together, the material naturally breaks into many dense pockets. Each pocket can then collapse independently into a star, leading to the formation of groups that emerge together, gravitationally bound. These clusters often contain stars of many different sizes and masses, from massive, brilliant blue giants to small, dim red dwarfs, representing a diverse stellar family. The newly formed stars interact through their gravity and intense radiation, profoundly shaping the immediate environment around them. Young, massive stars, in particular, create strong stellar winds and emit intense ultraviolet light that carve out vast cavities in the surrounding gas and dust. These powerful processes can either trigger additional star formation in compressed regions or halt it by dispersing the necessary material, acting as a complex feedback loop. Once the gas and dust are cleared away, the newly formed cluster begins its slow, collective drift through the galaxy. Over time, some clusters remain intact and tightly bound, while others slowly dissolve, their members dispersing into the general galactic field. Studying these nurseries reveals how the Milky Way continuously renews itself, building new generations of stars in waves of creation, a perpetual cycle of cosmic rebirth. As certain stars near the end of their lives, they undergo dramatic internal changes that cause them to shed their outer layers into space. These layers, often composed of gas and dust, expand outward, forming large, glowing shells of gas that elegantly surround the dying star. The shells appear luminous because the remaining, exposed core of the star heats the ejected gas, causing it to emit a soft, ethereal light. These elegant structures are known as planetary nebulae. Though they have nothing to do with planets themselves, the name comes from their often rounded, planet-like appearance in early telescopes. Each planetary nebula carries unique and intricate shapes, meticulously formed by the star's rotation, its powerful magnetic fields, and the complex motion of surrounding interstellar material. Some nebulae form perfect rings, others take on intricate, butterfly-like forms, and still others appear as simple, spherical shells. Over time, the ejected gas disperses into the surrounding space, enriching the interstellar medium with elements that were created inside the star through nuclear fusion. These shimmering, ephemeral shells represent a brief but incredibly beautiful phase in the life cycle of low to medium mass stars. They provide vital clues about how stars evolve and how they contribute new material to the galaxy, acting as cosmic fertilizers. Their delicate, luminous structures transform the quiet, graceful death of a star into a luminous event that ripples outward for thousands of years. A final, beautiful farewell. Among the many stars in the galaxy, some shine with an unusually rich, deep red color. These are known as carbon stars, and they possess atmospheres uniquely filled with carbon compounds that efficiently absorb blue light, allowing deep crimson tones to dominate their emitted spectrum. They form when aging stars, during a late stage of their evolution, dredge up carbon from their deep interiors and release it into their outer layers. This process dramatically changes the chemical balance of their atmosphere and gives the star its distinctive, ruby red appearance. Carbon stars often appear especially bright in infrared wavelengths, making them stand out prominently in surveys of the galaxy. They also produce significant amounts of carbon-rich dust, which then enriches the interstellar medium, contributing to the formation of new stars and planets. Studying these stars helps astronomers understand how elements, particularly carbon, are cycled through stellar evolution, from stellar interiors to interstellar space. Their deep red glow adds a unique diversity to the Milky Way's vast population of stars, showing how different chemical processes can profoundly influence the visual appearance of starlight. These stars burn with a warm, gentle, and deeply resonant radiance, offering a reminder that even small changes in stellar composition can create dramatic and beautiful effects in the light we observe, a subtle cosmic artistry. Many planets, in their orbits around their stars, are locked in a peculiar gravitational embrace known as tidal locking. In such cases, the same side of the planet always faces its parent star, never turning away from the light. These tidally locked worlds have a permanent day side, perpetually bathed in searing starlight, and a permanent night side, frozen in perpetual darkness. On the day side, temperatures can become extremely high, hot enough to melt rock, while the night side may be frigid, with temperatures plummeting far below freezing. A narrow region between these two extremes, known as the twilight zone or terminator, can maintain more moderate, potentially habitable conditions. Atmospheres on these planets, if they exist, would move heat around from the hot day side to the cold night side, shaping powerful wind patterns and clouds in ways that differ dramatically from those on Earth. Some tidally locked worlds orbit small, cool red dwarf stars, where the habitable zone lies very close to the star. Despite their unusual lighting and temperature gradients, these planets may still be capable of supporting liquid water under the right atmospheric conditions. Studying them helps astronomers understand how climates function when sunlight never shifts or sets, presenting unique challenges and opportunities for life. Tidally locked worlds demonstrate the immense range of environments possible in the galaxy. They remind us that the concepts of day and night, so familiar to us, can take on entirely different meanings elsewhere in the Milky Way, expanding our cosmic perspective. Towering both above and below the Milky Way's central region are enormous, mysterious bubbles that emit faint radio waves, now known as the Fermi bubbles. These colossal structures extend for thousands of light years, stretching far beyond the galactic disk, and are filled with highly energized particles. The bubbles likely formed from past, incredibly powerful activity near the central supermassive black hole, perhaps from energetic jets, or from bursts of intense star formation that released vast amounts of energy into the surrounding space. Their smooth, symmetrical outlines suggest that powerful, large-scale forces meticulously sculpted them, pushing gas outward into these vast, bipolar lobes. Observing these bubbles helps astronomers understand the energetic and often violent history of the galaxy's core. Inside them, charged particles spiral through powerful magnetic fields, producing the radio emission that reveals their shape and extent. The sheer scale of these bubbles is difficult to fully grasp. They rise far above the disk, forming some of the largest known structures in the Milky Way. Their presence unequivocally shows that the galaxy's center has undergone dramatic, episodic events that have profoundly shaped vast regions of space far beyond the immediate core. These giant bubbles act as colossal markers of ancient, powerful events whose echoes still linger in the quiet radio glow, a silent testament to galactic power. Black holes are often found not in solitary isolation, but in pairs, formed when two massive stars, originally part of a binary system, evolve together. As each massive star reaches the end of its life, it collapses into a black hole. The resulting pair of black holes then orbits a common center of gravity, slowly drawing closer and closer together as they lose energy. Primarily through the emission of gravitational waves, ripples in space-time itself. These hidden binary systems are incredibly difficult to detect because individual black holes, by their very nature, emit no light. Astronomers typically identify them indirectly, either by meticulously observing the anomalous motion of nearby stars that are gravitationally perturbed, or by detecting high-energy radiation when one black hole pulls material from a companion star, forming an accretion disk that glows fiercely. Some pairs of black holes remain quiet and elusive for long periods, revealing themselves only through subtle gravitational influences on their surroundings. These binary black holes hold valuable clues about stellar evolution, the dramatic death of massive stars, and the extreme conditions that lead to powerful gravitational wave events, which have now been directly observed. Their silent, intricate motion adds an air of profound mystery to the Milky Way. They drift unseen through the galaxy, locked in gravitational orbits that will eventually, in the far distant future, end in a powerful merger, releasing an immense burst of gravitational energy across space, a cosmic crescendo. Young stars often emerge from their birth clouds surrounded by swirling disks of dust and gas. These protoplanetary disks glow with a gentle warmth as the starlight from the newly formed sun heats the microscopic dust particles within them. The dust absorbs this stellar energy and then irradiates it in infrared wavelengths, creating a soft, ember-like glow that makes the disks visible to specialized telescopes. These glowing disks are the very birthplaces of planets. Over immense periods of time, dust grains within the disk slowly collide and stick together, gradually forming larger clumps that grow into planetesimals and eventually fully formed planets. The intricate structure of these disks can reveal the earliest stages of planetary formation. Rings, gaps, and spirals may appear within the disk as new, nascent worlds carve out paths through the dust, clearing their orbits. Observing these glowing disks helps astronomers understand how solar systems, including our own, emerge from simple clouds of material. They show that planets begin as tiny grains drifting in warm, swirling environments, slowly accumulating mass. These softly lit disks offer a captivating glimpse into the very beginning of worlds, shining as delicate, ethereal halos around the stars they nourish, cradles of creation. Scattered throughout the galaxy are enormous planets that drift freely through space, unbound by the gravitational pull of any star. These, rogue giants, can be significantly larger than Jupiter, our solar system's largest planet, and they wander through the cosmic void in profound, cold silence. They likely formed in young planetary systems, much like gas giants in our own system, but were later violently flung out by powerful gravitational interactions with other large bodies, perhaps during a chaotic early phase of their system's evolution. Once ejected, they continue on solitary paths, illuminated only by the incredibly faint glow of their residual internal heat, a dying ember in the dark. Some of these rogue planets may still retain thick, insulating atmospheres that trap this warmth, maintaining a degree of internal heat. Others may harbor swirling storms that churn slowly in the deep, perpetual dark, invisible to any distant observer. Detecting these worlds is incredibly challenging because they do not reflect starlight, making them incredibly dim. Instead, astronomers search for the faint infrared radiation they emit or watch for subtle gravitational microlensing effects when they pass in front of distant stars, temporarily magnifying their light. These lonely giants reveal how dynamic and chaotic planetary systems can be, especially in their formative years. Their very existence suggests that planets are not always permanently bound to the stars that formed them. Instead, they may roam indefinitely through the galaxy, traveling far from any warmth or light, true cosmic nomads. These wandering worlds add a quiet, mysterious, and profoundly solitary dimension to the Milky Way's vast population of planets, expanding our understanding of planetary destinies. In some binary star systems, a fascinating and often dramatic process unfolds. One star grows dense enough to begin drawing material from its companion. This stellar vampirism can occur when one star evolves into a compact object, such as a white dwarf, a neutron star, or even a black hole. The stronger gravitational pull of the compact object then strips gas from the outer layers of its companion star. This stolen material forms a swirling, incandescent disk, known as an accretion disk, around the feeding star, heating up to extreme temperatures as it spirals inward. This intense interaction can produce powerful bursts of radiation, appearing as bright flares in the sky, sometimes even X-ray outbursts. Over long periods, the feeding star may gain significant mass, dramatically altering its behavior, and sometimes setting the stage for future explosive events, such as a supernova in the case of a white dwarf. The star being consumed, conversely, may lose much of its outer envelope, profoundly changing its structure and evolutionary path. These dramatic, interconnected relationships reveal how closely paired stars can powerfully influence one another, demonstrating that stellar life cycles are not always solitary and independent. Instead, some stars grow by taking material from their neighbors, creating systems shaped by both cooperation and intense conflict, a cosmic drama. These feeding stars remind us that even distant suns can experience intense and transformative interactions, their destinies interwoven in a gravitational embrace. Although it may seem highly unlikely, planets can indeed survive the dramatic, often violent, transformation of a star into a stellar remnant. Some planets have been discovered orbiting white dwarfs, the hot, dense cores left over after stars like our Sun shed their outer layers. Others circle neutron stars, which form from the catastrophic collapse of much more massive stars. These environments are incredibly harsh, often flooded with intense, high-energy radiation. Yet, Some planets endure, a testament to their resilience. They may have formed after the star's death, coalescing from leftover debris in a second generation of planetary formation, or they may have migrated inward over time, finding a new, stable orbit. Around white dwarfs, a planet can eventually receive stable light and heat once the remnant cools sufficiently, potentially allowing for renewed habitability. Around neutron stars, conditions can be incredibly extreme, with powerful magnetic fields and bursts of radiation profoundly influencing the planet's atmosphere. The very presence of planets around dead stars challenges many of our assumptions about planetary survival and the conditions necessary for formation. It shows that worlds can persist and even reform, even after dramatic cosmic events that would seemingly destroy everything. These planets offer invaluable insights into how systems rebuild themselves and how diverse planetary environments can be, expanding our understanding of cosmic resilience. They serve as powerful reminders that even the aftermath of stellar death can give rise to new and surprising structures, a continuous cycle of cosmic rebirth.